Best new. Okay, welcome everybody to the CS-6515 office hours. My name is Joves. I am one of your head TAs. Generally, my office hours are to go over the material somewhat in the beginning of each topic, but it's actually mostly focused on going over practice problems, especially the ones that's given to you in class. So I'll go over the solutions. Generally, I just take the solutions that you already have. I'll post it, and then I'll talk about it on why the solution is the way it is, how you could, arrive at that solution. Hopefully, through enough practice, you'll be able to recognize that and do well on the exam. So that's the focus of these office hours. This office hours and all office hours in this class between myself and Dr. Brittle are all recorded and shared at the end of the office hours. So you should be able to. Oh, stop sharing my. Just double check. Huh. Okay. Yeah, I think Microsoft's doing this new thing where, like, once you start recording, it disables everything, because if you started your camera or mic or screens before the recording, it wants you to make sure to that you want to be recording that. So remind me if things don't go well when I do that, because I'm still getting used to it. So like I said, yeah, the point of the office hours is to go over practice problems and some of the material. This will be recorded. It will be shared. So if you decide to speak up or turn on your camera, or even, I think the chat actually also gets recorded. So that's just a disclaimer. I haven't had any issues with anybody, wanting to retract or redact what they say, but, just be aware. Yeah. The topic that we are covering this week is dynamic programming. So dynamic programming in this class typically can be one of the hardest topics for students. There's a few reasons for that. One, it's the first topic. So when you start a class and you're not quite used to the pace or used to the format of the class, it could be you're just getting used to the idea. The other thing about dynamic programming is that it's not super intuitive. Of all the topics that we teach, I think dynamic programming and then also NP complete, which is the final topic in this class, it's not obvious. Whereas when someone tells you about divide and conquer, or oh, this is what this graph algorithm does, and you just know the input and outputs, those are a little bit more intuitive. Whereas dynamic programming is like, okay, you want to get to a solution, but you have to build up all the subproblems before and up to that solution. You don't immediately tackle the problem that you're trying to solve. You have to tackle all the problems before it. So it's not a very intuitive way to solve problems. So it gets a little bit getting used to. Okay. So we have 3 parts for a full dynamic programming solution in this class. So the first part is the subproblem definition, which is you take what the problem is when it's presented to you, and you want to reward it in that you are solving for one specific subset of your problem. Okay, so that means that most of it is actually just sort of a pattern or a it's just a task that you do. I often think that every student should get full credit for subproblem definition, because you absolutely do not need to know much about dynamic programming to get the subproblem correct, as long as you pay attention to the cues and you pay attention to what you're supposed to write down. So you want to reword the problem for part of the subset, and then you have to decide whether A of I must be used or A of I can be ignored. Different problem calls for different situations, and that's probably the only real tricky part to the subproblem definition. And we'll go over examples that show whether you include I or whether you don't include I. And so it normally looks in the format of you reword the subproblem. I'm looking for the LCS. I'm looking for the least common, the longest common subsequence. I'm looking for the longest increasing subsequence of whatever you're trying to do in the subset of A of 1 to A of I. The reason why you have to state that is because your subproblem definition is focused around part of the problem. If you say, oh, I'm just looking for the longest increasing subsequence from A of 1 to A of n, that means that at every single table entry you have at I, you're able to solve the full problem, which is with the A of n, right? And so because that's not actually the case, if you say A of 1 to A of n in any of your subproblem definitions, that's going to be a mistake. Ravi, I see your hands up. I'm going to try to get through this slide and then ask if anyone has questions at the end of each slide, so I don't interrupt my flow. So I'm like ignoring you totally. And then you can say if A of I can be dropped, which means that A of I is not necessary to include in your subproblem definition. So if you're looking for, say, the longest increasing subsequence, you may be able to skip A of I. If you're looking for the longest increasing substring, you may have to include A of I in your in the calculation of your subproblem. And we'll go over that. But this is the really like the most like the part where you have to figure out. Everything else is just sort of following the format and pattern. Okay. And then the other version of this is you reword the problem, and then again in A of 1 to A of I, which includes A of I, which means that A of I must be used in the calculation of your results. Second part is you define the recurrence of the subproblems. You have to include a base case. The way that recurrences work is that it keeps looking back through your previous subproblems. But at some point, one of your subproblems cannot look back, right? Because if you keep looking back, you just go back forever. So you need a base case to stop your recurrence, which says, at t of 0, t of 1, t of 2, whatever your base case may be, I have already declared what that solution is, so that when I'm going t of I is equal to t of I minus 1, and then t of I minus 1 is actually equal to t of I minus 2, and so forth and so forth, I get to a point where, okay, this solution is already solved as a base case. You have to include the range, okay? So your recurrence is based on some starting point and some ending point to find your final solution. If you don't include a range, there's nothing to start or stop the recurrence, right? It's kind of like a for loop. So you always need a range on this recurrence. For the sake of written solutions in this class, when it comes to dynamic programming and most of the topics, we index our inputs from 1. Why do we do it? Because the book does it that way, and because the lecture based on the book does it that way. So our problems are done that way. It's also kind of helpful when it comes to later topics, especially in divide and conquer, to start with a input of 1. And so this can be a mistake, and if you don't index from 1, you're going to lose points. And when we hand you the input, when we say based on the input of A, it'll be indexed from 1. So that's actually very clear to you on the input. So if you try to access A of 0, that becomes a non-defined element. But the thing is, your table, specifically the table that you designed as your subproblem definition and your recurrence, you can index from anywhere. So if you need a t of 0 in order to set up a base case, that's perfectly allowed. If you need a t of -1, t of -2, that's all allowed. Consider your table to be more like a mapping rather than an array, and you can start from, you can index into wherever you want as long as it has been declared. So if I was to say, t of 1 is equal to t of 0 something, as long as t of 0 was set to something, that's allowed. If t of 0 was not set to something, that's when you could have a problem. So like if you don't properly set up your base case t of 0, and then you say t of 1 is equal to I minus 1, which ends up at t of 0. T of 0 not being set is a mistake. T of 0 being set, you're all set. Okay. Students asking, can we start from index 2 and set index 1 as base case? Absolutely. You can start from anywhere you want in your recurrence. As long as you get the right solution. You can set a base case at anywhere you want. As long as you get to the right solution, you'll be fine. Okay. You do need to use mathematical notation. We do not allow for code or pseudocode for dynamic programming solutions. So you need to use math notation. There is a post on it that will go over that. It should be DP recurrence relations. This is a really well-written post by one of our head TAs. So go ahead and read that. And just so you know, all the different posts that go on ed that are considered supplemental material are written by a various combination of your head TAs. David is the only one that really posts those. They're not all written by David. So when you ask a lot of questions in those posts, you may get a different TA that wrote that the contents of that post answering your questions. So that's why that happens. Okay. And then let's see. So yeah, do not reference unset values, right? If values are not been set before your recurrence happens, then they're invalid. You cannot do a self-reference, okay? So with mathematical rotation, you can't do something like, T of 1 is equal to T of 1 plus 5, okay? Because when this is being set, this doesn't have a value. It doesn't hold a value, so you can't do anything about it. You can do this in code if T of 1 is set to something already, but you can't do this with mathematical notation. The other thing is that you can't set conflicting values. In math, there's no sense of saying, oh, A equal, oops, my handwriting is terrible on the mouse. It's terrible in general. A equals 5 and then equals 7, okay? You can't do that. You can't set A to something and then set A to something else, okay? That's a conflicting value, and there will be points lost on that. What you can do is you can do A equals 10, and then because of some other reason, you do A equals 10 again, and then because of some other reason, you do A equals 10 again, right? Like this is declaring the value, but because none of them in conflict, this can be okay. You don't normally do something like this, but there are some examples where when you go to set T of I with a range, you want to set it to 0. And then you want to set T of I with a different range, and you want to set to 0. And if those two ranges have a overlap, it's okay in those situations because you're setting it to 0 both times. But if you're doing T of I equals 0 for some condition and T of I equals 1 for some condition, if those two ranges for whatever reason overlap, you now have a conflicting assignment, and that's not okay. So that's basically why that's okay. Right. And then C is your implementation analysis. So once you have declared what each subproblem is, and you've declared how each of those subproblems are solved, we want you to analyze that implementation of your dynamic programming solution. So first, we want to know how many subproblems your solution uses. So your table is generally, if your table is, a one-dimensional array, it's normally O of n. If it's a two-dimensional array, it's O of n squared. If it's a three-dimensional array, it could be O of n cubed. Whatever it is, you have to base the tell us the number of subproblems. Second part is state the runtime to fill this table. How much this actually can be different than number 1, and you have to be very careful when that happens. I will say that this right here, the number of subproblems in the big O notation is the floor of this right here. So in order to fill an O of n O of n table, O of n subproblems, you have to do O of n work at least. You can never do less work to fill a table. This is hopefully a obvious computer science idea that the least amount of work you can do to fill a table is how many slots there are in the table. Now, that's your floor. You can potentially have a higher runtime to fill the table than the number of subproblems in the table. So if it takes you O of n to figure out the solution to each subproblem, and there's O of n subproblems, your runtime to fill the table is O of n squared, whereas the actual number of subproblems is O of n. So that number of subproblems is the floor, but it can be higher to fill this to fill the table itself. And then we want you to tell us where the final return value is. Sometimes it is the last element in your table. Sometimes it's the max of the entire table. Sometimes it can be some T of 1, comma n if it's a two-dimensional table. We want to know how you extract that. And then we want you to tell us the runtime of extracting that. If it's just one single element, it's going to be T of 1. If it's some max of some row or some column or some part of the table, then you have to read the entire row, column, or the entire table to figure out what the max value is. And in that case, you would have to tell us what the runtime for that is. Okay. All right. So looks like there's a lot of questions. So I will try to go over them. All right, let me read off the questions in chat first. Will the notes be posted on Ed? They will not be, but the recording will be, and you will be able to watch the recording. Answer that one. Student asked, the range would typically go only in the recurrence and not the subproblem. That correct. Your recurrence always has to be in. Your range always has to be in recurrence. You can put it in the subproblem and you won't lose points for it, but it actually doesn't have any value in there because the subproblem definition is at the instance of T of I. And the T of I is defined no matter where I is. So saying that I is defined between 1 and n doesn't really have any value. You don't lose points for it, but you could potentially accidentally forget to put it in the recurrence. So I just suggest only doing it in the recurrence. In the subproblem definition, should we have a range? Just covered that. You probably shouldn't. Yeah. If I struggle with mathematical rotation, what are some resources I should look for? You can look. I say you should just use the Ed discussion post because that should cover all uses of math notation you need for this class. You could potentially just look up math notation on, say, Wikipedia or online resources, but that will be way above and beyond what you need, and it could potentially confuse you because there are some things that we don't allow in this class. Not that the math notation is invalid, we just don't allow for certain, mathematical shortcuts, if you will. So I would just pay attention to that post and ask questions in the post if you have any. A TA will get back to you. Okay. Universal quantifiers allowed. I don't think there's ever really a situation where you need it, and I don't think it would really be valid. So I would say, not that it's not allowed, I just don't think you'll use it, and I don't think there will be a context where that would be correct. So like I said, if you the scope of mathematical notations in general is way bigger than what we need, and it could potentially get in trouble if it's just it's not what we are looking for. Okay, so say I'm doing something like min of j conditional where 0 equals j of m. What can I do to state an otherwise condition? You state the otherwise condition, right? So like if you have what's one saying? If you have a condition that you are trying to get a minimum of, and you potentially could not get a proper solution in that min, you just say otherwise do this, and that's how you handle it. And I think we'll have a problem with that, especially with knapsack problems. Typically with knapsack problems, you say, give me the minimum or maximum of this for every coin, or I'm sorry, not for every object that is less than this weight. But looking for, and so you just have an otherwise and you say 0. Okay, so that's how we would do it. Okay, you guys keep asking questions, so I can't really stop. Okay, there's like a bunch of questions. I am going to stop because there's too many, but I am going to answer some of the live questions. Robbie, go ahead.
Hello, Joves. Can you hear me?
Yes.
Thank you, Joves, for telling us about the dynamic programming guidance. What I wanted to do is go back a little bit. Before you start talking about subproblem definitions and such, I think you gave some advice on how to write the subproblems in general. Did you say that it would be a good idea not to write down scenarios before you write down your subproblem? Because that's what I did when I was trying to do the homework, right? I was trying on the homework, I wrote down scenarios for the two examples before I proceeded to try and write down a subproblem and my recurrence. Do you understand my
I
question?
didn't say anything. I didn't say anything about how you should what you should do before and after. This part right here is just to say what you need to write down for your solution, how you come about the solution. If you want to work through subproblems, if you want to draw a table first to figure out what those recurrences would be, any sort of strategy you have is perfectly fine as long as it works for you. I will go over some of the strategies I use, but there's nothing wrong with writing on scrap before you decide to write down what your solution should be.
Okay. I think that explains enough. So I mean, I was thinking that for my approach, I would try to write down a subproblem and then figure out work out the scenarios before writing down my solution. Or maybe I'll try that. I'll keep on doing that. Maybe.
No problem.
All right, thanks.
Jeff. Don't know how to pronounce that name, so I apologize if I butcher it. Jafar?
Yes,
Jafar?
this is Jafar. Yeah, Jafar?
Jafar.
Yes.
Okay.
Yeah, you can call me Jeff, it's fine. So I have three small questions. So the first one, first of all, before my question, thank you for those office hours. I think they are very beneficial to us. But for my questions, so first of all, for the base case, so the base case, sometimes you are defining T0 equal to something, but I read somehow, sometimes they are defining the full table and they put, for example, zeros in the full table, then they start computing and fulfilling the table. I'm coming from a Python background, so we don't need to do that. We always append, and that's it. But I remember that MATLAB does not work like that. Here in the base case, should we start by defining the full table and putting, for example, somehow a value in each place of this table before start computing it?
We will show some practice examples, and I will go over that. But you do not need to declare. You do not need to declare a table before you use it. So this is very much not code. Okay, you'll keep that in mind. You do not need to declare a table before using it, and you do not need to declare any values that you don't use. But you do not have a default value. So if you were to create say, in code, if you were to say a array of integers, right? Like most of the times, those will have a default value. That doesn't happen here. Even if it's a 0, you have to set that value anytime you are going to access it. It has to be declared for it. But you don't have to say give me a table, append to it. You just assign the value that you need, and it'll be available.
Okay, so from the base case, I can just assign T of 0 and then continue, and then inside the problem, if I'm only using T of 0 as a base case, that's it. This is good.
Yep.
Yeah. Okay. My second small question. So what the difference between 1 and 2 here in the implementation analysis? Because here we have the number of subproblems in big O notation and then the runtime. Is it the runtime, not big O notation? What's the difference? So what's the difference?
So the runtime, the second runtime should also be in big O notation. I mean, I can update that in a second so that it's so that it doesn't get confusing that it's different.
Okay. Okay. Till now, maybe you will explain that later. But till now, 1 and 2 are very confusing to me, because while I'm doing 1, I'm already saying that this is, for example, of n squared. This is, for example.
So I covered this. That the number of subproblems is the floor of the runtime to fill those table entries, but it is not always the runtime. So, for example, if you went over the knapsack lectures, right? One of the things is that the knapsack lectures have a you can use unlimited the objects, and there's 2 ways to do it. There's one that's that uses a 2-dimensional table, so it's the table size is the b times n, right? And then there is the one where you don't need to keep track of your items because they're unlimited. You just have a table of size t of b, right? So it's a single dimensional table. So the size of that table is O of big B. But the runtime to fill that table remains the same whether you do the simplified version or not. It is still O of n times b. If you were to say that the table size is O of b and therefore the runtime to fill that table is O of b, that would be wrong. It still takes O of n times b to fill that table.
Understood.
Right.
Okay, understood. Finally, One second. Yeah, the runtime at the end. So the return, whenever you are returning, let's take the example that I have to go over, for example, the diagonal of a table. And then the value in the diagonal of the table will be the maximum value will be the answer. So this is basically O of n. However, if I am while filling the table, taking that output into consideration, so having a maximum and updating it each time it's occurring wherever I'm fulfilling the table. This will help me in the output to get O of 1 to get the output. Here, should I say,
yeah.
Yeah,
So
tell me.
so a couple of things. One, that's perfectly fine in code, but you can't do that in math notation, right? So like I said, if you did something like, max equals 10, and then you go, you do an if statement, and you do max equals 11 instead, you're now having a conflicting problem with max, and that doesn't work. If you wanted to, you could keep a separate table and just constantly update it until the end. You could do that and then do that T of 1 if you really wanted to, but that's like, extra work when, if your runtime to fill in the tables T is O of n, and then to extract the solution is O of n, you haven't done anything that would make your runtime any slower. So it's the easier solution, but we will look at how you extract the maximum and your big old runtime to extract that solution based on your presented solution. So it's not like, oh, we can do it in O of n, and you did it in O of 1 because you did the work ahead of time. With that, we wouldn't mark you wrong for that. So it's up to you.
Okay.
There's just simpler ways to do it.
Understood. Okay, thank you very much. Thank you very much.
Yep. Okay. I'm gonna answer one more questions and then move on. Alejandro.
Hey, just quick question. So in the base case, when we're saying T of, let's say, 1 equals 2, can we reference one of the inputs, say T of 1 equals to P of 1 or A of 1?
Yeah, absolutely. And you're almost always going to have to do that. Yeah, you definitely have to use the input in some way to set your recurrence. Otherwise, otherwise it wouldn't be a dynamic programming problem if the input
No, but
didn't matter.
I mean in the base case, is it
Yep.
allowed to reference? Okay, thank you.
Yep. You can have T of 0 equals A of 1. That's fine. Or some, yeah. You can absolutely reference the input however you want, however you need. Okay. All right. So I'm going to go over the strategies of how to solve dynamic programming problems. Hopefully you have all watched the lectures and read the book and understand all the different type of dynamic programming problems that you will encounter in this class. So from there, the best way to solve dynamic programming problems is to actually be able to look at the problem and figure out what kind of problem it is. This is true for a lot of different algorithm problems. Like at the very high level, you look at a problem and goes, okay, is this a dynamic programming problem? Is this divide and conquer? Is this a graph problem? Is this something I can solve using a various different algorithm approaches? Luckily, in this class, when you're given a problem, you are told exactly what topic that problem is in relation to. So when you get on the exam and you see a problem, it'll say solve using dynamic programming, or they'll say solve using divide and conquer, or say solve using graph algorithms. So once you know that this is a dynamic programming problem, the rest is just recognize which version of the dynamic problem there is. There's a handful that we teach in this class. There's more advanced ones. There's variations of them. But for the sake of this class, you only really need to recognize a subset of them. Okay, and then you start with that generic solution. Generally, you take, if this looks like an LIS problem, take the skeletons of an LIS solution. If this is an LCS problem, take the skeletons of an LCS problem, and then you fill in the requirements or the details for that specific problem to solve it. Okay, so what do these problems look like? So here are some patterns you should recognize. Note that these are general principles that you can use to guide you. They're not going to be 100%. There are going to be some problems that you look at and you're like, ooh, it's kind of LIS, but it also could be LCS. I'm not sure. There's some problems you're going to see that's going to be, ooh, this is kind of like knapsack, and this is also kind of like a windowing problem, which is, my word for describing chain matrix multiplication type problems. So when you get to that, it could be one, you're missing some detail on figuring out which is the right approach, or two, some dynamic programming problems can be solved using multiple approaches. It is important to be able to sort of recognize it, but this is just sort of a guide, right? It's not an absolute way of finding these. Okay. Okay. Someone wants me to go back. Yeah, just start with a generic solution, and then learning the lectures. Okay. I'm going to try not to go back too many slides because the entire thing is recorded. If you miss something, just take a note that, oh, I missed slide before this, and then just go look in the video, and I should be able to look at it. So LIS, if the problem only has a single input array and you're not comparing to anything else, then it's probably going to be it's possibly an LIS problem. Some of the different problem types will share some of these traits, and so it's important to just kind of figure out which of these problem types a problem has most of the traits of. So a CMM type problem might also have a single input array. So kind of be careful, but if it's a single input array, then you can consider LIS as an approach. If the problem is comparing the input to itself, if the problem only looks back one element at a time, not a window or a bag. So window is an indication of CMM type problem. A bag or a container or a partition is an indication of knapsack problems. So if you're only looking at one element and you're comparing that element or considering that element in some way, it might be an LIS problem. This is normally, but there are exceptions, a 1D table. Okay, you can generally solve these with a single dimension table. So they have O of n subproblems, and then there are two variations to LIS. O of n lookback. So this means that if your subproblem needs to consider all previous elements, it has to consider all the previous subproblems up until that point. You need to look at, you're trying to look for any previous element that's greater than or less than typically. This results in O of n squared runtime. You're going to have O of n subproblems. Each subproblem is going to take O of n to solve, and so you have O of n times O of n giving O of n squared runtime. Okay. There's the O1 look back, which is the second variation, that if the subproblem only needs to check one element back, you're dragging the best solution down with you. Okay. So you're checking a constant number of elements back, or you're checking a constant number of subproblems back. If the restriction moves forward with I, so like you're looking for the longest common subsequence, the longest common subsequence. Substring. The longest common substring. You're always basing on your very previous subproblem, so you don't have to keep looking back. So it's a little bit faster. If the subproblem needs to carry the max, sum, count, etc. forward, you end up with an O1 look back. And then since the subproblem carries the answer forward, you don't have to look back the entire subproblem table. And this results in O of n runtime. If every single subproblem can be solved in O of 1, and you have n subproblems, then you have an O of n runtime. Okay, so that's LIS. Any questions particular to LIS and how to solve them? Brianna?
Hi. When with O1 look back, you said if the subproblem is to check a constant number of elements back, I think you mentioned that this can happen in longest common substring, and I thought that a common substring, I'm assuming, has two different inputs, maybe X and Y. Why would that be an example of, or an example of this?
Sorry. I misspoke. I meant longest increasing substring. Sorry about that.
Okay,
longest
cool.
increasing
Thank you
substring. You would because you always have to continue on a previous substring. So you only have to look right immediately back to say, am I greater than the previous number? If not, then I start over. So you never have to look back, right? In a longest increasing subsequence where you don't have to that when you're allowed to skip, you're looking for the previous best answer that you can attach yourself to. So you always have to look back at all the previous subproblems to see what you can attach to, and that ends up being a O(n) look back.
Okay, thank you very much.
Yep, no problem. Stephen? Or Stefan?
Yeah, sorry, really quick. This might be kind of obvious to ask a question, but basically in the previous thing, we're able to so set like A, for example, if we have different conditions, like we can set A to like 2 separate values, like A equals 1 in one condition, and then like another condition, we can say, we can say A equals 2 in some other condition. Because in your previous example, you just set them all to 10, so I didn't know if that was a thing or anything, but we should be able to do that too as well, right? That's something we can do.
Yeah. If your TFI is set based on conditions, that's fine. You just can't set TFI again once TFI has been determined.
Right, of course. Maybe I'm overthinking it because it seems like obvious, but yeah, it's like it's pretty straightforward. I got you. That's good.
Yep.
All right, thank you.
Edgar? Edgar? You're muted if you're talking.
Okay, I apologize for that. So the question is, in some of these problems, it may be beneficial to have a dynamic variable to keep around to see the state of the current entry. Is that a valid kind of aid to introduce to the definition of the problem? Like, you may keep track of things depleting or a range of things just diminishing or expanding. That are not necessarily, you don't need to have a full table to keep track of, but a dynamic variable would do the trick.
Yeah. In code, you absolutely would do that, but with mathematical notation not allowing you to reassign a variable, you'd have to keep it in a table if that's something you want. Okay. And it doesn't hurt your runtime, so it doesn't matter. Oh, one thing I should mention is that space is unlimited in this class. So you can, when you are solving a problem, we never look at, other than how many subproblems you have on your table, we don't look at spacing, right? So we don't care if you use a whole table to track a value, or if you use a single. Well, we do care if you use a single value, because if you use a single value, you're constantly reassigning it, and that's not allowed.
I see. That's helpful. Thank you.
Yep. I'm going to answer one more question and try to move on. Joseph?
Hey, can you hear me?
Yep.
Hey, so based off some conversations on Ed, and I just want to clarify to make sure I understand. So it seems like with code, we might be able to achieve an O of n time, but in mathematical notation, we can only achieve an n squared time. And we should stick with the mathematical notation, right?
That should not be the case. There should not be a case where code would get you a faster runtime than the mathematical notation. If that's the case, then I would consider what is causing that discrepancy.
Because the example is for the homework, and I'm not speaking too much about the solution. Someone did propose an O of n solution where it used like a pointer that they moved along, and based off of this definition of the O of 1 look back, the restriction did move forward with I, but it required a pointer. It required a programming construct to do so. So in code, I could see how that could be executed as an O of n, but based off of the recurrence tools that we have available, and Jamie said, it wouldn't be a valid recurrence to say this is O of n. It would have to be O of n squared. But just so there's just a little bit of confusion from me on that.
Okay. First, if Jamie says no, then
yeah,
Jamie, because
I understand
Jamie
why
ultimately
it's
decides how it's graded, but I would have to take a look at a very specific problem. The way I see it is that if you're trying to track a pointer going forward, right, and writing and reading from the pointer is all one, right? Let's just, without knowing anything about what the solution is, if reading and writing the pointer is all one, and every time you read and write from it, it's all one, and you want to do it, as you move forward, there's nothing stopping you from creating a table for the sake of writing this one single variable at each I, right? So like, you know, let's just say my variable, instead of writing it to one single variable, I write it to a table with variable, and then via 1 I write something, and via 2 I write something, and via 3 I something. That is potentially a single O1 read and write each time. So I don't think there's anything in mathematical notation that would stop you from doing that if you wanted to track a pointer. That being said, if you're doing something where like the entire solution is done mathematically, that might be what would stop you from being allowed. Like we don't want you to solve any of these problems with like a single math equation. Even if it's possible, we want to avoid that because we're trying to teach you dynamic programming. So I'd have to look at the very specific question that's being raised. Yeah.
I can send it to you later, but I appreciate you.
Yeah, put it in my office hour thread and then tag me and I'll try to take a look.
Sounds good. Thank you.
Yeah. I'm gonna move one over. Hopefully your question will still be relevant on the next slide. I don't want to keep stopping for too long. Okay. All right. So LCS is the next one that you typically learn. So if the problem is comparing between two arrays, so if you're looking for the longest common something between two arrays, if the problem is looking for something in common, so you're comparing things to see if you can track something. This is normally, and there are exceptions, a 2D table. You need to track your comparisons as you move forward on one array versus the elements on the second array. So you end up comparing every single thing in the first array to every single thing in the second array. And it can be O of n_m or O of n squared subproblems. Why different? What does this mean? Well, if you're comparing two arrays of the same length, then you end up with O of n squared. If you're comparing two arrays of different length, one of length n and one of length m, you're comparing every single combination of the first array with the second array. So that becomes O of n_m. So it's basically the length of one array times the length of the second array. If they're the same length, then it's O of n squared. Don't quote me on this, but I feel like if you wrote this, technically right. Looked weird, technically right. So if you want to remember it that way, if you can, but I would just write O of n squared. And there are, again, two variations of this. There's a substring version, which if the subproblem needs the matches to be consecutive, so you need to have every single, in the longest common substring, it has to be consecutive. So in that case, what you're doing is you're adding 1 to or whatever. And when I say whatever, this goes into how the next type of problem works. So you're not always adding 1. You might be adding 2, depending on what you're comparing. You might be adding some kind of value, depending on what you're comparing. So typically 1 when it's LCS, if the comparison succeeds. And then, so, this is what you look like. It looks like T of ij is equal to 1 plus T of I minus 1, T of j minus 1. So you're adding 1 to the previous best substring. Okay, and the previous best substring is I minus 1, j minus 1, because, you're shifting your pointer forward. So if you want to add 1 to it, you shift it back 1 to add it to. You reset to 0 when the comparison fails. Because you're looking for consecutive matches, it has to be a substring. The second that you break up that matching, you immediately reset. You no longer can continue the previous best. So you immediately reset to 0, and then you start adding 1 to it again for every match that happens afterwards. And so it's your T of I j equals 0. Okay, and the solution is the max, because you are calculating the longest common substring along your entire comparison table. Your longest common substring could be like the first 10 characters of both strings, right? So your size of is 10, and then every subsequent character does not match, right? But because you're tracking the longest common substring at each I and j entry, your final entry in your table might be 0, but there's a match of 10 characters at the very beginning of your two strings, and therefore you want to look at the entire table to see what the max is. Okay, The second variation is the subsequence, and this is when subproblems are allowed to skip mismatches. You're looking for a subsequence, which is, you can do like, the first 3 characters skip a bunch, and then the next, 2 or 3 characters skip some, and then next several characters. So you're trying to compare based on a subsequence. Okay. So same situation. Here, you add 1 if the comparison succeeds, right? So if the comparison succeeds, you take the previous best subsequence, which is I minus 1, j minus 1 again, and you add 1 to it, or whatever you're trying to add. But if it fails, now you want to know what the previous subsequence was, if you are allowed to skip a match. If you're allowed to skip a match, then it is the max of my current I in the previous j, or my current j in the previous I. Because mismatches are allowed to shift your comparison, you now have to check what the best possible solution before this was. And before this, it's either we just say, okay, well, T of I and j doesn't match. I'm just going to skip j and keep going. Or I'm going to say T of I and j doesn't match. I'm going to skip I and keep going. And the decision on which one to use depends on what the best previous solution was. So you're going to take a max with that. Now, your solution, because this right here carries forward your best solution, because you're allowed to skip characters, your solution is always going to be carried forward. Your final result is either going to be T of nm or T of nn. And again, this is the difference between whether you're comparing the same length input or two different length input. And so your solution is always at the very bottom right of your table. Okay. Questions regarding LCS? Edgar?
I don't know what happened. I don't currently have a question. Thanks.
Okay. So there's a question in chat about extracting a final response by backtracking through a table. Can we do an insert before operation in a mathematical valid way, or should we just create a second table and keep track of the length of the result and start back from index 1? So in terms of writing a written solution, we typically don't ask you to do any sort of backtracking. So you don't have to really worry about that. But if you had to do backtracking, you could potentially keep track of it as you're solving, or just go back and using the information of your solution, your table, and your input. You're generally able to backtrack all the way to get the full solution. But when you're asking for like an LCS, your answer, the question is going to ask you what is the actual number of the longest common subsequence or substring, rather than give me the longest common substring or give me the longest common subsequence. In code, it's a little bit different. We feel that, like, you have more time with the coding problems. So the coding problems typically ask for a full backtrack solution. But on a written problem, in homework, on the exam, we typically don't ask that. Okay. Okay, I feel like I've been answering this question like many times. You cannot keep updating your maximum value, because you can't do that in mathematical notation. You have to do it in the table if you really want to do that, or just do a scan of your table at the end. It does not matter to us whether extracting the final value is O of 1 if your entire algorithm is O of n. You're not saving yourself any time right there. Okay. Okay. Going to hands raised. Bikash.
Yeah, so we have this 3 options here, right? I minus 1, j minus 1, which is when I and j are maybe equal. But then we could have I minus 1, j minus 1 when they are not equal. And we don't have that version here because there are some problems of I, j minus 1 or I minus 1, j. Is that understanding correct?
So I'm going to go back. Okay. So it turns out that entire comparison actually can, if you had to and wanted to, be written as oops. That is way too thick. Okay, that actually is what it could expand out to. I'm going to leave it up to you to discover this, but I will tell you that no matter what, no matter how no matter what these three values end up being, it turns out that T of I minus 1, J minus 1 will always be less than equal to the max of T of I minus 1, J, and T of I, J minus 1. Okay, so that's to say that the max of these two values that we are already checking because of the way the recurrence is set up, the max of these two values will always be greater than or equal to T of I minus 1, J minus 1. Okay, and because of this relationship, you actually can just drop this out completely when you go to check what the best previous one was. Because if you think about it, when you have a if I have 10 consecutive characters that match 10 consecutive characters, whatever, right? When I'm at my 11th character, 11 compare if these two don't match, then the longest subsequence between 11 and 10 characters or 11 and 10 characters will be greater than or equal to the longest common subsequence between the 10th character. Because worst case scenario, I'm just going to take this number and I'm going to move it forward and say this one doesn't. This one is dropped, and so I'm still carrying this maximum number forward. And then I can also say, well, this one doesn't get us anything, so this one can be dropped, and I'm still carrying the best solution of these two forward. So this one right here will always be less than or equal to the max of the top two, and it doesn't matter. That is to say, if you roll out the whole thing, it actually still works, but you don't need to because there's no reason to. Does that make sense?
Yep, thanks.
Cool. Okay. Any other questions? Okay. Is it correct that for the subsequent type problem, we do not require x of I, y of j to be included in subproblem definition, and for substring problem, we require it to be included? Yeah. So in the subsequent version of this, because you're carrying your maximum forward, you may not include the last two characters in your subproblem definition. Not that you cannot, but you may not need to. Whereas with the substring, you're always looking for what the best possible solution is that includes your x of I and y of j. Then those two must be considered when you are calculating your longest common substring. So hopefully that was in the lectures, and that should be what I just said. Okay. All right, we're gonna move on. Oh, so runtime again, O of n times m or O of n squared. Similarly, if you're comparing similar length problems or different length problems. So the number of subproblems in this case actually does match up to the number of the runtime. Whereas when I set the LS problem, notice how I have end up what's it? Both of these problems actually has an O of n subproblem, right? But because this one does O of n work on each subproblem, this is O of n squared runtime. and this is an O of 1 look back each time, so this is O of n runtime. Notice how I, very clearly that the number of subproblems is the floor of both of these runtimes, but it is not the same always. Okay, so you need to be careful about that. That's why they're given to you as two different questions. If they're always the same, there wouldn't be a point of asking you both questions, right? All right. 6. All right. So the next problem that we're going to cover is edit distance. This is not covered in your lecture specifically. It is covered in the textbook, and sometimes we assign problems that are very similar to edit distance. The reason why this is fair, even though it isn't in your in the lectures, is that it is actually just a variation of the LCS problems. Okay, it's very similar, and you can consider this a third variation. Okay, so if you're again comparing between two arrays, if you are looking to minimize differences between two arrays, or if you're looking to assign some penalty to these differences, or if you are assigning some points to any matches. So any type of problem that that has one of these three ideas behind it, it tends to be an edit distance problem. Okay, and you're trying to align two arrays. Okay, and this is again normally a 2D table similar to the LCS problems. There are exceptions, of course, but this is what you normally do. Same number of subproblems as before. Now, what you are trying to do is you're minimizing or maximizing the score when you're matching I and j. So we have T of ij is equal to min max of, depending on what the problem is asking, T of I minus 1, j minus 1, plus some functionality of ij. And then you're saying T of I minus 1, j plus some functionality of ij, and T of I, j minus 1, some function of ij. Okay, basically you declare a function to determine the value, penalty, etc. of unlining I and j, and then you try to find the optimal position to put I and j in order to get those points that you want. And the final solution is T of n min, T of n. Okay, again the runtime is the same. Now, one thing you might consider is that LCS is actually just a simpler form of this third variant or edit distance. Okay. If we were to take this wow, that was like a little harder to erase than I thought. All right, let's try this. Okay. And we said instead we are going to add some function of ij and add some function of ij. And we add some function of ij. Okay. And then what we're going to say is that f of ij, this function that we are declaring, equals 1 if x of I equals y of j. Okay, equals 0 otherwise. Right? So what does that get us now that we turn this LCS into an edit distance problem? What it's going to do is say, well, if the two matches, I'm going to add 1 to the previous best, right? If we match, we add 1 to the previous best. If they don't match, I'm going to add 0 to T of I minus 1 j, and T of I j minus 1. Once I have set that all up, I'm just going to see what the largest value would be. And it turns out that if it matches, this is going to be the largest value. If it doesn't match, like I said, these two values the maximum of these two values will be greater than or equal to this value when this is 0. So this is actually what the edit distance problem would look like if you were to set it up to solve LCS. Okay, and so it's kind of cool, I think. Yeah. So LCS edit distance is just a more general version of LCS, really. Okay. Any questions about edit distance? Let's see. Reese.
Yeah, so this function, would we define that in the base case section?
Generally, in any sort of edit distance or alignment type problem, that function will be given to you arbitrarily, and it'll just be, there's a function that does this. And so you wouldn't even have to know what that function does. You wouldn't even have to declare it. It'll just be given to you. That being said, you can define helper functions in your recurrence by saying, let function f be this, and you can describe how it works similar to what I did, and then use that helper function in your recurrence if you want.
And that helper function you're saying that would be in the base case part, or just anywhere, doesn't matter for that section.
It's in your recurrence. I mean, in your recurrence, there's no separation of like what the base case is and the rest of the recursion is. I would just declare. Yeah.
Okay. Thanks.
All right, Garrett.
Hi. So in LCS and edit distance, due to the thing that you just described, we can drop the third term of I minus 1 and j minus 1 if we explain that correctly, if I'm understanding you correct.
For edit distance or for LCS?
I suppose both, because of what you just stated, where like the first two terms is greater than or equal to I minus 1 and j minus 1.
So for LCS, you definitely can and probably should drop the I minus 1, j minus 1 term. For edit distance, you can't. You don't know always what that function would do on a match, or what that function would do on a non-match. One way to do edit distance is to do a penalty. One way to do edit distance is to do a reward. And so that last term, which I minus 1, j minus 1, could be less than, could be greater than the other two terms. I mean, the other two possibilities, depending on what the situation is.
Got it. Thank you. That was well explained.
Yep. All right. All right. You're gonna move on. I'm actually gonna take. So it's been an hour. I'm gonna give everybody about a 2 to 3 minute break to use the restroom, and then I'll come back and cover edit distance. No, sorry, now it is knapsack. So go ahead and take a break. I'm going to give everybody about another minute or two. How's everybody enjoying the class? Fun? I hope.
It's very fast-paced.
Yeah, it can be. I
would
understand
agree
that.
with that.
I think it's good. I like it.
Good.
I was surprised. I thought it'd be harder, but I mean, I don't know. I've done a ton of leak code problems, so maybe that helps me. This.
Yeah, I think if you have a lot of experience with leak code, it puts your mindset in a way to sort of like recognize, because like leak code is all about pattern recognition, recognizing the pattern of what the problem is, right? So it puts you in the mindset to like kind of recognize these. And like I said in the beginning, like to solve dynamic programming problems, it's all about recognizing what type of problem you're trying to solve. And then after that, you just set up the skeleton and fill in the details. Like it's once like it's I know it's like it's a very silly paradox. Right? It's like if you know what the problem is asking you exactly, it's really easy to solve the problem. And so that's what you should be trying to train your eyes and mind into.
Yeah, I find doing the problems a lot of fun, actually.
That's good. Yeah.
I think this session will help, but I wish there was more official solutions so that I could grind the problems more, because like I need a lot more problems to start seeing the patterns. I kind of recognize patterns slowly.
Yep. Yep. Yeah. We offer official solutions to the practice problems that we give, and then for each topic, Dr. Brillo will add additional practice problems where you sort of work out on your own. And the idea is for you to work with other students to sort of come up with your own few of the solutions. We find that if we offer we do both, right? Because we find that if we offer official solutions to every single practice problem, a lot of students will look at the official solution and go, oh, yeah, I could have arrived at that solution. Therefore, I understood the problem. And that's not always the case. And it gives students like, maybe like a false sense of security. The other thing is like, you write a problem, you write a solution. And it's like, oh yeah, it kind of looks like the official solution. It's pretty much the same thing. And then you go into like, the exam thinking that you've solved it on your own when you really haven't. That's why we like to kind of break it up. Some of them you get an official solution for. The other ones you just kind of have to, get that intuition and actually present your solutions to other students so that other students can be like, yeah, that looks right, or no, that doesn't look right. So that's the strategy between the two, I think.
Yeah, that makes sense.
Do you is there gonna be possibly maybe more questions that more questions we can ask, like a larger pool of questions, or is it basically if you can do the homework and do everything, you're pretty much fine, you're just good? Are the other questions?
The general approach to it is that you absolutely need to do the homeworks. The homeworks are going to be what the exam is going to mostly kind of, it's going to be like, we gave you these as homework problems. So these are the fairest problems or fairest similar problems that you will see on the exam. The practice problems are also very fair. The practice problems with the solutions, we say, hey, these are the problems we want you to be able to solve as well. And here are all the practice solutions, so you know what that solution is. So in terms of like, a priority, I would do your homework, do the practice problems that have official solutions. And then if you have time, and as well as for, better prepare you for the exam, do all the other extra problems that are given. Even if we don't give you solutions for them, I typically will go over them in office hours so you can get a general idea of how to approach those problems. All right.
Yeah, definitely.
With that, I think it's time to start the next section. So I'm going to start knapsack and then again answer questions at the end of this. So with knapsack, if the problem is checking to see if something can fit or add up to. So a knapsack problem is another variation of knapsack problems, which you might see is called the subset sum problem. Subset sum problem, SSS. It's a very famous leak code type problem, which is can I add a bunch of numbers to some sum? It's actually a knapsack problem in disguise. Try to figure out why that is, but it is the two problems are very similar. In fact, both problems are NP complete or NP hard problems, and they actually reduce to each other. So that's sort of a preview of what you'll see in the very final topic of the class. If the problem needs a maximum value for a specific budget, if the problem is trying to find a minimum budget needed for a specific value, there are two variations to knapsack problems that we cover. So there's limited items. So this is normally, and there are exceptions, again, a 2D table. You have all of NB subproblems that you're trying to fill out. For each increment of the items, you want to know for each increment of the budget if the item can fit. Okay, if the item can fit, then you see if adding that item by removing the weight needed to fit that item is better than the current value without that item. Okay, so this is what that equation looks like when you are able to try to fit this item into the budget you are trying to calculate. You want to know if the same budget, before I is considered, is worth more or less than removing enough room to add the new item. If it can't fit, then it doesn't matter. You're just taking whatever the best previous value was, because this item can't fit. It can't be considered for this budget. So it's as if the item was never even considered. Don't worry about it. Okay. And this all results in O of NB runtime. It takes this many calculations to fill this many subproblems. Okay. And I'm going to continue. David, I see your hand up, but I'm going to finish the knapsack slides and then I'll call you. The second variation of knapsack is if you have unlimited items. You can take an item and you can reuse that value and budget over and over again if you want. Okay. The main difference between the limited and unlimited is that we don't check I-1 because we don't care if it was considered or not. Okay. And this is normally, and there are exceptions, a 1D table. It actually can be a 1D table or a 2D table. It depends on which version you want to write. Some students find that the 1D version of this table easier to recognize and easier to understand. Other students like to solve it using the 2D table because it's so similar to the limited items that you can just make a slight tweak and it just fits the second version of the problem. Do whichever one you feel more comfortable with. Both will be accepted. Yeah, can be 2D if you don't simplify. It's either all of NB subproblems for the 2D version, or it's all of B subproblems for the 1D version. Okay. For each increment of the items, for each increment of the budget, if the item can fit, we want to know, once again, what the previous best answer was. What the best answer is by removing enough items to fit this item and its value. Okay. And we are just going to keep, we're just going to do that for all the items. That's it. We don't have to know what happened before this item was considered because it's valid. We don't care how many of these items we use, so we don't have to track that. Okay. And then, oh, this is what another student is asking for is if you have a max function and this ends up in an invalid state, right? Let's say our budget starts at 1 and I have nothing that weighs, that has the weight less than 1, because that would be 0. What is my answer? What will happen to this function? This function actually doesn't have a correct answer, and so I need this 0 otherwise, which is saying if this function right here, if this max function doesn't give a satisfying answer, then just set it to 0. Okay, and this is how you set that up. Okay, and the way this equation works is you want to know if the same budget before the current instance of the item is concerned, not the current item, the current instance is worth less or more than removing enough room to add this instance. Okay, and then if the item can't fit, again, you don't do anything, as if it don't consider it, just move on. And this is all NB runtime. Again, this number of subproblems or this number of subproblems is the floor to your runtime, but your runtime may not always match the number of subproblems. This runtime remains the same no matter which version, version of this the solution you write, but the number of subproblems can be different. Okay. All right. Questions about knapsack, David?
Actually, I have a couple questions. One is about the first one, or it's more about the 0-1 knapsack. That I feel like I have this gut feeling like I don't understand why it's position invariant with the items, and sometimes I can convince myself that it is, and sometimes not, and I'm not sure why. The second one is it seems fishy that the one with unlimited items has a simpler solution. and I don't understand how that's possible.
First of all, it's not a simpler solution. It's just a more concise solution, if that makes sense. Like the complexity of the problem does not change regardless of which version you do, because you're doing it. So let's see if I can try to draw this out.
Oh, and also, what goes in the table? Like, I don't understand what's in the table for the unlimited items one. Like, what is the value of the subproblem represent? Is it just the maximum value at a weight?
Yeah. So imagine, if you will, I have a bunch of, I have this big bag, right? I am trying to fill out this big bag with as many items as I can jam in there, right? And so when you are trying to do this, when you're trying to do this at home, you're trying to fit into your suitcase, and let's say you have all these items that you want to put in. So you're trying to jam. You probably do a greedy approach, right? Like you're not running an algorithm in your head when you do this. You're doing a greedy approach. You're trying to jam all the high value items in there. I need my laptop. I need clothes. I need I might not need shampoo because the hotel might give me a shampoo. You're jamming all the really important stuff in there. And you get to a point where you are out of room. You can't put anything in there. So once you're out of room, you still have a tiny little bit of space. You're like, oh, I'm going to put some low value items in there because, be greedy. Make the best of the room that you have in your suitcase. Why leave anything out if you can jam low value items in there? So that's a greedy approach. It doesn't really work for an optimal solution. The other thing you do is that you jam your suitcase to the max. And you're like, if I take out my razor, I could potentially fit in a toothbrush, a comb, and some shampoo. Now, the razor is worth more than any of those 3 items, but because those 3 items make up, end up with more, more value together, I'm willing to give up my larger razor and put that in there. And so that's basically what the knapsack problem is: trading out value and space to see if you can get more value in for the same amount of space. So when you're going through each item and going through each budget, you're saying, okay, let me find an optimal solution to this, even if it's not a greedy approach. A greedy approach will get you pretty close, but it's not an optimal solution. What you're going to do is you're going to take a very small bag. You're going to say, okay, I have this tiny version of a bag, and I'm going to figure out what the best value I can jam into this bag is. So if I can jam, my pills, that's it. That's all I can put in there. That's the only thing that's small enough to put in there. I'm going to assign this bag a value. So next, what I'm going to do is I'm going to take a bigger bag. Okay, and there's you can imagine this like incremental like bags in between these. But for visualization's sake, I'm going to say, okay, well, I can put a small bag, one of these in here, the same value in of that space, and I can put it in here 4 times. Okay. And that's one possible solution when I consider this. But I at some point also calculated this second bag, and I also calculated this third bag, right? And now I'm saying, okay, well, what happens if I started off by saying, okay, I'm going to fit 4 of these bags. What if I take these out and I fit whatever would have fit the second bag in here? What if I do that and I say, okay, well, what if I take this out and I fit what would have fit here instead? Now, whether these things are bags, which has multiple values in them, or a single item that is of that size with one singular value in there, doesn't really matter. You're just trying different things out. So what you're saying is, okay, for every time I have an item I want to consider, let me remove enough space of this current bag that I'm thinking of and see what else I can put in there that has a high value. I'm going to try everything. At the end of that, you now have a best solution for this bag, this bag, this bag, and this bag. Now, when you get to your final bag, you're basically saying, okay, I have all these smaller bags already calculated that I could use as my best solution. And now I have this one, I have an item that's, again, this size, this size, this size, whatever, okay? Every time I have this already pre-calculated what I think is the best solution, I'm going to take out enough room to fit this item. But I know all the previous bags maximum value. So all I have to do is look back at the smaller bag, see what that value is, and add the value of this thing. The next item is a little bit bigger, and I want to look back at a size of the bag that I've already figured out the solution for that can also fit this item, and then add those values together to tell me, is this a better value than if I try to fit this in? Okay. Now, these items aren't like sorted in any way, right? So potentially you could start with this item first, you could start with this item first, and this item first, and this item first. It doesn't matter because all your smaller bags have been calculated up to this point. You can at any time access what a smaller bag value would be plus this current one item you're considering. And that's how the knapsack problem plays out. You're calculating the value of every smaller bag such that you have access to that optimal value every time you want to calculate a new item at a bigger bag size.
So
hopefully that makes sense for knapsack.
So in terms of the invariance of the object order, is it a good way to think of it is like every time you're looking at one object, adding one object at a particular weight, when you're subtracting that weight, like all the prior weights have already been accounted for. Those are the subproblems that have been solved.
Exactly.
So you don't have to worry about the current row of B, the other objects in the current row. Okay,
perfect.
Cool.
That's exactly right.
Thank you.
Yeah. The reason why dynamic programming works is that when you build it from the bottom up, anytime you have a later subproblem, that later subproblem is dependent on your solutions of the prior subproblems. And because you've already solved every prior subproblem, you always have access to the information you need to solve the current subproblem. That's how the bottom-up approach works. All previous subproblems is needed in some way, and it's already been solved.
Cool.
Yeah. And so when you have an unlimited supply of items, instead of going through like each item once, what you're basically saying is that, okay, I have this same size box, right? Normally, if I only have one item of these, I'm going to try to jam, my comparison is between this one and this one, or this one and this one, right? Those are the only two configurations I have based on these three items, right? So this is how I'm going to try to put them in the box. But what you're doing with unlimited items is you're saying, okay, well, with this box, I'm going to compare this to this to this, and so forth and so forth. You are going to go through an item, and you're going to keep trying to see if I all these configurations, what is the best solution. And so I no longer need to track whether this item was considered or not, because I don't need to know if I can reuse this item. That's the whole point of tracking the I-1, is to know that what was the best solution before this particular item was considered, because I can only consider this particular item one time. If you don't need to track that because you can use the item unlimited times, you end up with not having to track I-1. You just care about what was the best solution for B before, if I subtract the weight of this item from B, what is my best solution if I add it back in versus what was the best solution for B previously. So you're just using that as a T of B is equal to max of all the items you can consider.
And all that we're solving for in this version is the maximum value of the items in the bag. Like we're not recovering what were those items. Right.
Because you don't care. You don't care. You're not tracking which of those items, if you've used that item or not. So the I-1 can be removed. You don't care. The runtime is still the same. You just don't need to track anymore. You don't need that information. You have to think about your tables when you're setting values on that just being information to retrieve. If the information to retrieve is irrelevant, you don't have to track it, even if you spend the work to calculate the information you need. You don't have to track that I dimension of the table because you don't care.
Okay, thank you.
Yep. All right. Other questions? Try to answer that. Jafar?
Yep, this is me another time. Sorry, but I have two
Good.
small questions. The first one, you said that we can do whatever we need, either the one table or two table, and maybe one is optimal more than the other. Will we get more points if we do the more optimal solution, or no? It's not the problem for this course.
For the sake of written problems, we don't care about your big O runtime, right? So if it's O of n, it's O of n. If it's O of n squared, it's O of n squared. It doesn't really matter to us if it's like O n squared plus so many steps, O of n plus so many steps. It's just the big O notation, and that's the only thing we care about. Doesn't matter how much space you use, doesn't matter. For the sake of the programming problems, because programming problems have real life implications and it's interesting to us, when you get your programming grade back, we run your solution against a model solution, and the model solution is written with some not super optimization in mind. It's written in such a way that, like, I as a software engineer know that a lot of writes add up, so I try not to write if I don't need to. I know that using space has allocating space, reallocating space has real life consequences, whereas in a written algorithm it doesn't. So you're being compared against a model solution that one of the TAs have written, and it's just interesting to you, right? It's interesting to you because it's unweighted. You're not going to lose any grade, but I'm sure as software engineers, people will be interested with, well, I implemented the algorithm with the same big old runtime, but it's a little bit slower than the real life optimal solution. I wonder what I could have done to improve my code. So it's just for interesting cases.
But I'm asking more about the exam. Yes, if we are talking about the runtime, so if I have done it in O of n square runtime, but someone really has done it in O of n runtime, this will he get better than me?
Yes.
Yes.
If the absolute big O runtime is better, you are probably going to lose points. And two things. One, it's based on our target runtime. We have seen problems where we think a very clever, very complicated solution could be O of n, but the solution that we want students to arrive at is O of n squared, and you give us an O of n squared solution, and another student gives us O of n, you'll both get the same points on a problem that we think that a particular runtime is really tricky, really difficult, that we're not looking for. That's one thing. The second thing is suboptimal runtimes has different penalties depending on the problem and depending on the topic. For example, just arriving at a correct solution in dynamic programming is most of the difficulty, right? So we put a little bit less weight on the overall runtime. As long as you give us a correct solution, you will get good score. You'll lose a few points here and there because of the runtime, but you'll get a score that you should be okay with. When it comes to divide and conquer, it's the opposite. Divide and conquer problems are really, really easy to solve with brute force. It's very easy for you to tell me, for you to find a number in a sorted array, right? You could just brute force it, read it from beginning to end, find the number. That's so trivial, it adds no value to your understanding of algorithms. So a lot of the weight of divide and conquer problems is actually shifted towards the optimization of your solution. So you can lose a lot of points if you don't do an optimal solution on divide and conquer. So it depends on the problem. Don't look at your dynamic programming solution going, oh, I was suboptimal, I lost a handful of points. But when I went to the exam and I did divide and conquer, I did a brute force solution, I lost almost all my points. Like, what's up with that? Like, depending on the type of problem, there's different weights on optimization.
Okay, thank you very much. A final small question about knapsack. For the unlimited items, here I know for the limited items, the greedy solution will not work. So it's not the optimal solution. Maybe you will get a better solution. not even better in terms of runtime, but in terms of correctness. So it is not correct. But for the unlimited items, in my opinion, I think greedy is correct. Is it true or not? Because I asked also the
No.
same question for our professor. No, okay. Do you have a counter example, for example, or something? Because till today I'm not being able to find. Because greedy is basically we are getting the best option for each item and then try to put it inside the full box.
Yep. So like I said, if we a lot of students will try to do a greedy solution to knapsack because it's intuitive. I'm going to fit all. So you what a greedy solution for knapsack would be, right? And this is actually interesting topic because it will be it'll come up later on in NP complete problems. NP complete problems, NP hard problems are considered really hard problems to solve optimally. So getting that optimal solution is not always the best way to do it. And that's how you end up with approximation algorithms, which is to say that the amount of time to get the optimal solution is not feasible, but an approximate or a good enough solution in a very fast runtime is as good as the optimal solution, and people are going to be happy with it. The approximation of a knapsack is actually just a greedy solution. You take all your best items, you shove that in first, and you're looking for the best. Your best items isn't the highest value; it's the best value to weight
Right.
Right. So like, yeah, the best value I get in there, shove that all in there. Whatever room I have, shove the second best item in there. Whatever room I have, shove the third best item in there. That doesn't end up working because at any given point, you could potentially take an item, right? Let's just say a very simple solution, right? The best way to disprove whether something works or not is to just take the simplest contradiction to it, okay? Suppose I'm trying to fill this box, right? And I have this item, okay? That fits in there perfectly, right? And we're looking for some ratio, right? Of points. Let's say, this is 2x, okay? 2x multiplier, it's pretty good, right? Now suppose I have this right? These two are the same. This has a 2.1x multiplier. Okay?
Yep.
And you would think, okay, well, 2.1x is better than 2x, right? I'm going to start shoving 2.1x items in there. But what's going to happen is the 2.1x doesn't quite fit in there. It doesn't quite take up all that room. I can put two of them in there, but if I put in two of them in there, I'm left with this space, okay? And that space doesn't allow me to put the 2x item in there. But I can put the 2.1x in there and have some value, okay? But because this is only a ratio, it doesn't give me the absolute value. So it turns out that by losing some of the 2.1x multiplier, by putting the 2x in there, I fit more of that room, right? And that gives me a higher overall score. And this can happen at any point with a greedy solution. At any point of the greedy solution, you end up putting your highest ratio in there when it's not the best solution. It's good enough in an approximation maybe, but in terms of a pure optimization solution, it's not okay. You have to put the 2x in there, even though it has a lower multiplier, because it fills up more space and gives you more absolute value. Does that make sense?
Okay. Oh yeah. Okay. I need to think about it. Yeah, but I understood your point. Thank you.
Yeah, and I will say that in terms of knapsack problems, the approximation in general will be a very subtle difference in the absolute best value and a good enough value, and this is why a lot of like real life problems that uses approximation that uses knapsack would use an approximation greedy algorithm in real life. But in terms of the class, when we're saying we want the optimal solution, you got to go with the the full knapsack solution, which is NP complete.
Thank you.
Okay. One more question, and then I want to move on to CMM. Bradley?
Yeah. My question is when translating, I guess some problems can be translated directly to a version of 0, 1 or unlimited knapsack. And then you could just do the exact algorithm for 0, 1 or unlimited. In that case, the subproblem definition doesn't really match the problem definition at times. Is that okay?
We do reductions in this class in later topics such as graphs and in NP complete. For dynamic programming and in divide and conquer, we want you to solve the problem directly without reduction. So your subproblem definition has to match the problem that you're doing. What you can do is take what you know about the knapsack subproblem definition and reword it to fit the problem that you're actually trying to solve. But you can't do something like, this is basically a knapsack problem, so I'm just going to give you the knapsack solution. And in our heads, in our mind, yeah, this reduces to the knapsack problem, but you have to solve it directly when we're on the dynamic programming topic.
One of the answers to one of the homework problems reduces it directly to knapsack, and in that case, the subproblem does not represent the problem. Is that
so I will
okay?
be solving. I'll be solving some of that, and you can bring up questions. So the coin change problem, right? Yeah. I'll solve that, and then we can talk about it.
Sure.
Okay. Cool. All right. And then, so I think this is the final type. This is the windowing problem. So this is what I call the chain matrix multiplication. I describe it as windowing because that was the way another student, when I took the class at the time, explained it to me, and I thought it was so much more intuitive than trying to do understand CMM. So I call it windowing. It's also a lot easier to sort of illustrate, which I'll talk about and show in a minute, but we'll go over what these problems are. These are probably going to be your most difficult set of problems, but hopefully when you recognize it, you can just set up the generic skeleton and then fill in the requirements, and it should still be pretty okay. So you're doing a windowing check, and I'll explain what that is a little bit later. If the problem is asking for the most efficient way to split an array or split something or multiply something or set up something. If the problem is asking, split in some way, this is normally, and there are exceptions, a 2D table. Potentially could be more dimension than that, but typically this is set up as a 2D table. All of n squared subproblems, and there are two variations, of course. So you're only doing a window. So you start at a window size of 1 to n, and you are going to set your I to go from 1 to n minus window minus 1. So the reason why you have to do this is because, so like say you have this entire array you're looking at, and you are going to look at a smaller window of, say, this size, right? Well, you can't just take I, which is the head of your item, and shift it all the way down to the end of the array, because otherwise you end up, taking this window and shoving it right off of your the size of your array. What you want to do is you want to shift it so that it ends up right about here, right? So where is I anchored to at this point? Well, it's n minus the size of your window, and then minus 1 for indexing purposes. But it's 1 to the end of your array minus the window size, so you have leeway. And then you set j, you anchor it to be I plus the window size. So if this is your I, then this is your j, right? And so it turns out when the window size is correctly calculated, the very final window, your j right here, is going to be equal to n, right? Because if your I is set to be n minus window minus 1, and your j is going to be that I plus the same amount that you subtracted, then your j equals n. And that's how your windowing works. You take a window of a certain size, and you shift it through your array to get the best answer for that window. That's important because of what we do with that window. I want to leave that up, but hopefully you can read this. So you calculate T of ij using smaller windows between I and j. And remember, the way that subproblems work with dynamic programming is that all smaller subproblems or previous subproblems have already been solved. So anytime you have a large window that you need to divide into smaller windows, those smaller windows, much like the knapsack bags, have already been solved for you. So you can use that information to solve for the bigger or later subproblems. Now, absolutely. And this we can do then because the window is growing and all smaller subwindows, which is I and j minus 1 or I plus 1 and j. However, whatever the smaller windows are, no matter where their position is, all smaller subwindows have been already solved, and therefore, no matter what their position is, as long as you need it, it'll be there for you to calculate. This will result in O of n squared runtime. So this is only on the windowing part. Okay. There's a second variant to it, which is the windowing and the breaking of the midpoint. This is what chain matrix multiplication does. This is what I believe the optimal binary search tree does. You're looking for a window plus where to break in that window to get the optimal solution for that window. So this, to me, is the hardest class of dynamic programming problems that you will see in this class. It could be super intuitive to you. Then in that case, another problem might be difficult. But in general, for students and for myself, this is probably the most difficult of the problems. So again, you're starting a window size of 1 to n, and you are going to again set I to the same, the same thing where before you're moving the window, so similar situation, and then you're going to anchor j to the end of that window. Okay. Now, when you are calculating that large window, you're going to set a breakpoint k to between the start of the window to the end of the window. You're basically trying to decide or compare where that breakpoint should be to give you the optimal solution for the full window. And you track what that max would be. You don't track it in the table. I mean, you could, but you don't need to. You don't need to track it in the table because you're just going to keep trying different k's until you find the optimal solution for T of ij. Once you have the optimal solution to T of ij, it doesn't really matter to you where the k was in order to get this optimal T of ij. All you have to do is track the optimal solution to T of ij. Whatever k was can be tossed out. You don't need it. And this be done because as the window is growing, you have all the smaller subwindows. You have the subwindow of T of I to k, and you have the other subwindow T of k plus 1 to j in order to make a decision on what the best T of j is. This results in O of n cubed runtime. Okay, because you have O of n squared items in your table, but within each of those tables, you have to shift k through between I and j. That number of subproblems within those subproblems is O of n. So you have O of n squared subproblems. Each of those takes O of n time to calculate. You have an O of n cubed runtime overall. Okay, and that is how that works. And with that, I want to illustrate, and hopefully this helps you visualize it a little bit better. And again, pardon for my horrendous handwriting and drawing skills. Okay. So you start off with this array, right? And you're trying to find out, the question is, how can I break up this array into pieces such that I get the maximum or minimum of something? You're trying to calculate what the best way to separate all your this piece of array is. It may be that you don't do any separation. It may be that you only do one separation, whatever the requirement is. Well, in order to calculate this piece, I need to calculate what the best value is for what the value of this is and what the value of this is, value of this and this and this, and that's how I calculate the value of the bigger piece. So what you want to start off with is you want to go, okay, well, I'm going to start off with a window size of 1, and I want to calculate all the solutions I have for window size of 1. Okay. And depending on the problem setup, this actually could be an optimal solution. I'm just going to cut my thing into tiny little pieces, and that results in my best solution. Maybe, maybe not. Now you want to know, what is my best solution for all the size 2 windows? Well, my size 2 windows is dependent on whatever I need to calculate between these 2 smaller windows. So my first size 2 window is right here. Okay, so this has some value assigned to it based on these 2 values. And you're going to think, well, my next ones are going to be this way. Okay, and it turns out that's not the case, because you are calculating for all possible size 2 windows. So the correct way that this actually ends up being done is I'm going to shift over 1, and this is my next size 2 window to calculate. I'm going to shift over 1 again, and this is my next size 2 window to calculate, and so forth and so forth. So you end up with every size 2 window calculate. Okay. Now, with that information, I can settle for all size 3 windows, because my size 3 window is going to be a combination of some size 1 window and some size 2 window. And because I've solved all the smaller subproblems, I have every combination of that solved. So when I go and decide the value, I can just take care of that, right? So I'm going to, if I have a size 3 window, it's going to be right here, right? And this turns out to be, if I can draw a little bit better, sorry about that. Oops. Let me see if I can correct this without ruining everything. Okay. This red window is either going to be calculated with this and this, right? Or it's going to be calculated with this and this, okay? I have two ways of calculating the size 3 window. And then the exact same thing happens as I slide. I have every single size 1 window and size 2 window, right? And then when I have 4s, I have every size 3 window, every size 1 window, and every size 2 window. All size 4 windows are some combination of a size 1 and size 3 or 2 size 2 windows. And I have access to all that information. So as my window expands and I slide that window across, I always have all the information before. Now, that is your O of n squared subproblems, okay? This comes out to be O of n squared. Where does that extra O of n come from? Well, when you have certain setups of the problem, I'm not just saying, okay, well, I have all the information from previous subwindows, and I can easily calculate my my size 3 window just by looking at small bits of information. I have to declare a k. Let's make it a little bit bigger so it's easier to visualize. I have to declare a k, right? That might possibly change the solution between if k is right there, k is right there, k is right there, etc. I have to try shifting this k down my larger window, and at every single breaking point, I have to go, okay, what would have been the best solution from the left, calculated with the best solution from the right, which I have access to. And that is where your O of n, your additional O of n work comes from, because you're trying every single breakpoint in between that window. So this gives you the O of n, and multiplied with this, you get O of n cubed runtime for the very complicated windowing problem. You get the O of n squared runtime if you don't have to try anything. If the answer is simply like a yes or no answer, and this is some of the example problems might do this, then you might do an O of 1 runtime for O of n squared subproblems, and you end up with an O of n squared overall runtime. But in the more difficult case, this is how you end up with O of n cubed. Okay. Is there any questions about how this works? Awesome. Oh, David, go ahead.
Sorry, I just wanted to clarify. So if we mapped this onto the matrix chain multiplication problem, what those green boxes would mean would be multiplying one matrix with the one next to it, and then when we're zoomed out and we're looking at the two, that would be the the blue boxes would be groups of two matrices that have been multiplied together in a previous stage, multiplied by a single other one before or after. Is that correct?
Yes.
Okay, cool.
Shunek.
Hey, hi, Joves. Thank you. I didn't follow in what situation we would have O of n square. Do you mind repeating that part, please?
Yeah. So let me take a look at your. Hold on. I'm going to take a look at your practice problems and see if one of them will cover. Okay, perfect. We will have a problem that shows that when it's open script, and I will call it out for you when we do the practice problems. It's actually the first practice problem that we're going to go over, so it kind of works out.
Okay, thank you.
Yeah. Any other questions? Okay. So I'm going to go over some common mistakes that students typically makes in dynamic programming problems. These numbers are estimates. They're kind of gathered across multiple semesters of me looking at grades. They can vary from problem to problem. Some problem has more difficult subsections in one part than other problems. In so don't take this as, oh yeah, I'm definitely going to make a mistake because of the problem type. It can vary, but general sense, an idea. When you have a suboptimal solution, there's going to be penalty. So we will grade on dynamic programming how correct your solution is, and then we take off a flat amount on a suboptimal solution. So that could range depending on how difficult we think the optimal solution of a problem is. But basically, you can get everything right about your problem, but if it's a suboptimal solution, you're going to lose points. Don't bother arguing with this. Every semester, students they'll just say, hey, I got the right problem. Why am I losing any points? It's good enough. It's not. It really isn't. A suboptimal solution can have harmful effects in both, solving the problem in computer science and in day-to-day coding, right? Like your employer is not going to be okay with you constantly getting the correct answer and slowing down the system overall. Optimal solutions has real value both in this class and in real life applications. So you need to learn how to do that. Subproblem definition, common mistakes. If you define the subproblem on the entire input instead of partial input, remember your subproblem definition is a look of what your what the solution is for that specific subproblem. If you give it as the entire input, like oh, this is the best answer for A for the entire A array, that is not true. If you say that this is the best answer for A of A to all the way to N, that is also not true. It is something to do with the ith input and something to do with the ith best ith solution in your table. So be careful. If you don't properly handle the ith item, either you include it when you don't need to, or you don't include it when you need to. This particularly is like I said, the most difficult part of the subproblem definition really is just this part. You're just repeating everything else, and this is the part where you have to focus on and be careful. So that's where a lot of students lose points. And that's the only two things really. Like there's only so many parts to the subproblem definition. Subproblem problem definition is 4 points. I think this is, for the most part, a free 4 points as long as you're paying attention. So you start off with 25% of your problem getting full credit as long as you pay attention. So, try hard. Defining the recurrence in subproblems. If you're missing the base case, you're going to lose points. And I think about 10% of students make this mistake. These percentages tend to go down by exam time because students will have recognized that they made a problem. And it's also a sort of a paradox, right? Like as I show you what these penalties are, less and less students make these penalties. So that's a good thing. So these numbers fluctuate. Not having bounds is a big one. Your recurrence has to start at some point and it has to end at some point. And so without the bounds, we don't know what that is. I mean, we know what you're trying to do, but that it's also never enough to argue on your regrade to say, oh, you know exactly what I meant. And while that might be true, your code doesn't compile and run just because people can guess what the code means. It's still a problem. It's still an error. You're still going to lose points. Indexes from 0 instead of 1. It's a minor penalty, but it's a minor penalty that is easily avoided as long as you pay attention and remember that the input is given to you from 1 to n. So when you access the input, you have to go from 1 to n. And notice that this is input. Input is the big key word here. Your table can index from anywhere. Your input is indexed from 1. Okay. Reference refers to itself. So if you do anything like t of I equal to t of I plus 5 or something like that, you're not allowed to, because t of I can't be set until you can't be accessed until you set it. So don't do that. Reference refers to unset entries. So if you, for whatever reason, accidentally skip some entries and you try to refer to it, that is a penalty as well. Assignments have a contradiction is also a penalty. And these are, you're looking at these like, oh, very few people make these mistakes. Well, some students make multiple of these mistakes. And as long as these mistakes have penalties assigned to them, they can rack up. You can end up with a solution that is actually very correct if you're just telling it to me. And I'll go, yeah, all the logic in your solution makes sense. But because your recurrence has all these mistakes in it, you might end up getting 0 points for a, in theory, working recurrence. So you have to be careful about these minor penalties because they can absolutely add up and there's only so many points to go around. Algorithm error, like you just straight up didn't solve the problem correctly. And it depends on the problem. Some problems will have multiple parts that we are looking for. And so each part has a smaller penalty. Some problems are really just one single part to get correct. And in that case, if you get it wrong, you end up losing more points. So it really just depends on the problem. Best advice I can give is just don't get it wrong, and then you won't find out what the penalty is, right? And then there's the implementation analysis. Incorrect, insufficient answer to extraction details is a surprisingly high. So we've only been doing implementation analysis for the last 2 semesters. So I just recently looked these up. This is actually surprising to me because it's just basically your return value, right? Like you've set up your table, so you're either always going to return, t of some singular value, or you're going to return some max or min of all your values. I guess students would just make the mistake and return the wrong one, but try not to make that mistake. Yeah, I'm a little surprised about how high this percentage is. Your subproblem count, you didn't count it correctly. So it could potentially be wrong, and then your runtime is incorrect. So that's some amount right there. So these two tends not to be too bad. Students typically are very good at counting how many entries in their table and how long it takes to do it. The extraction is I guess where a lot of students lose points. Any questions? Yep. Let's go with Manjaneta.
Hi, Joves. Thanks for taking my question. So regarding extraction of the answer, so I have a question about especially when we are solving the Elias kind of a problem. For some examples, the solution might work as a TN, but there can be other examples where the answer can be max of T. So in that case, is it safer to mention max of T star, or it has to be accurate that it should be either T of n or max of T of star?
So I don't think it's always the case that the max will happen to be the best answer. So that's one thing to keep in mind. But I will check with Tim, who is one of our lead graders. If I can get a solution as T of n, and I instead take a max of T, and I get the same solution, but it's not the optimal runtime, but it doesn't matter because my algorithm is already T of n, O of n. Am I going to lose points, Tim?
If it doesn't change the overall runtime, then they're equivalent. That's full credit.
Okay. So yeah, I would say that if you get to the point where you're kind of unsure, then yeah, you can take the max and then return your runtime based on that max. But if you return the max and you give a wrong runtime, you're gonna lose points. If you return the final item in your table and you give the wrong runtime, you're gonna lose points. But as long as those two match and the answer is correct and it doesn't impact your overall runtime, Tim says it's okay.
Good to hear. Thanks.
Okay. Bradley?
Is correctness of implementation analysis based purely on your definition of recurrence? Like, say, for example, you said this is a bad argument, but like, oh, I was trying to do X in my recurrence. Well, is my implementation based on what my recurrence actually says or what I quote unquote was trying to do? It's based on what it actually says, right?
So you're saying that if your extraction detail is wrong and you lost points there, is your runtime based on the extraction detail that you wrote or what the extraction should have been?
If your recurrence is wrong or like suboptimal, your implementation analysis should match your recurrence definition, right?
I believe that's true.
Okay.
Okay. Nicholas? Nicholas, you muted.
You mentioned the subproblem definition was worth 4 points. Do you have a breakdown of what part B and C is worth point-wise?
I do. I can, but I'm sure Tim knows the answer right away, so I'll let Tim answer.
I believe. Oh man, off the top of my head,
Tim,
I think.
Oh
I think
my
it's...
God, I have so much trust in you. All right, I can check. I have
262 is what I'm thinking on a 10-point DP.
Oh, that's right. Sorry. So yeah, it is 262. Sorry, I bungled that because it used to be out of 20 points. So this used to be 4 points. So this is worth 2. This is worth 6. And this is worth 2. Okay, 262. It used to be like 4, 12, 4, but because we've halved the total score, because like it was a little bit too many points for us to allocate, and we were just basically working based off a factor of 2. So like all the penalties would be like 2, 4, 6, and 8. So we basically just halved everything, so it was easier to grade and easier to give students their grades. All right, beyond this.
Yeah, I had a question just to confirm on the subproblem definition. A lot of the examples are using prefixes. If we use suffixes in our definition, as long as we're not using undefined variables, we won't be dinged for that, will we?
As long as you make it clear which way you are looping, and as long as you make it, it's very, we look at it and we go, okay, there are no undefined variables that you're trying to access. And we know very much like, okay, this is the way you are looping through your input read or your subproblem definition, and your recurrence makes sense, it's okay.
All right, perfect. Thank you.
As long as you follow the rules, no matter how funky your solution is, if it follows the rules and it's a correct answer, you will get points.
Okay, perfect. Thank you.
Jafar?
Yep.
This isn't the end of the office hours, by the way, in case you're thinking like, oh, I need to get all my questions in. There's more to this office hours. So,
yeah. But I think this is the only one for DP.
Sorry, what?
This is the only one for dynamic programming. The second one will be for the next next topic.
The next one will be for Divide and Conquer, but I do a exam prep office hours that will go over very quickly the information I want, just so students know that I've covered it before, and then I will be going over more dynamic programming problems for the exam prep.
Okay, thank you. So very small one for the algorithm. So you said algorithm errors. To my understanding, and what the professor said, we should not write any pseudocode inside. It will be like the homework. But how we understand my algorithm, I tried, for example, for the homework to explain in written. So what I will do, how I will do things, and some not pseudocode, but like say example of
You don't
how I
need
do.
so you don't need any of that, and it will be mostly ignored. The only thing we care about is the subproblem definition in words, the recurrence in
Okay.
mathematical notation, and the implementation analysis. Anything else added to it will mostly be ignored. And if you
Okay.
don't have a proper mathematical recurrence and you try to explain it in words, you will lose basically all the points because that's not what we're looking for.
Yep. Yeah. Okay. Understood. Thank you.
Yep. All right. I am going to give about a 2 to 3 minute break again, and then when we come back, we'll go over the practice problems. All right, I am back. Okay. All right, first problem that we will go over. Hopefully I am unmuted. Yep. Is going to be the dictionary lookup problem. So one of the things I like to do is sort of read the problem, talk about it a little bit, kind of high level overview of like, how I would have at the time when I'd solved all these problems, what I would have been thinking, how I determine what the pattern is, point a few things out, and then I will paste the solution that we have already provided you before. I think every Thursday we release the practice solutions, and then I'm just going to go over the solution and talk through it and give you an opportunity to sort of ask any questions. So the problem states that you have n characters, okay, which you believe to be a corrupted text document, and you lose all your punctuations, and so you want to reconstruct it into to see if it's a series of words, and you have a dictionary, and it's a Boolean function dict of the word. It returns a string, any string w for any string w. You want a DP algorithm that determines whether the string can be reconstituted as a sequence of valid words. The runtime should be at most O of n squared, assuming that calls to dictionary takes unit time. In the event the string is valid, make your algorithm output the corresponding sequence of words. So first off, we will not solve B because, like I said, on the written problems, we typically do not do backtracking. If you're curious about doing it, I recommend coding it. I think that would be pretty cool. And but if this was given to an exam, you wouldn't be expected to do the backtracking. The second part is that the runtime is given to you. We don't typically give the runtime for dynamic programming problems. We might give the runtime for certain other types of problems, but it's not something you should depend on. You should be able to solve these problems without knowing what the runtime is. And so looking at this, my initial thoughts are, okay, well, it's on an LCS because we're not comparing, two sets of arrays. It's not a knapsack because we're not, trying to fit or have value in budget type things. So it's neither of those. So what you're kind of left with is LIS and windowing. So we're not trying to find the longest of anything. We're just trying to find out if certain things are returning true and false. And what ends up happening is that you're looking at the smaller portions of your problem, such that you can't just simply look at everything from beginning to end. You're not looking at like, here's my array, and I'm going to be like, oh, my pointer moves here, my pointer moves here, so forth, so forth, and so forth. And that's not really what you're doing. What you're looking at is, if I took an array of letters, can I break this into multiple words such that this is a word, this is a word, this is a word, and this is a word? And when you do that, you're looking for all the, sorry, every now and then I get this error, all the looking at all the smaller subsets of whether this section right here can be broken down into words, or if this section can be broken down into words, and then overall this entire section can be broken down into words. And that to me screams this is a windowing problem. I am looking at smaller and larger and larger windows to see if every single window contains all valid words. And if this window contains all valid words, and this window contains all valid words, then this entire larger window contains all valid words. And then if this window contains all valid words, and this one, then this entire thing contains valid words. And then overall, this entire array contains valid words. So that is what I'm trying to solve. That's a windowing problem. Okay. So let us look at the 6.4 solution that has been provided to you. Okay. So what is our subproblem definition? So we are going to say, so you have to say what this is returning, right? So you need to know what this is set to. So you could say, you don't actually have to write true. The way the problem is asked is whether or not let's see, whether or not a string can be reconstituted as a sequence of valid words. So what you actually can also say is let T of I equal whether or not S1 to Si can be reconstituted as a sequence of valid words, right? The true and false here is helpful. It kind of tells you, gives you a better indication and better detail, but it's not really needed. So keep in mind, because I was telling you, well, what you can just do is re-say the subproblem, restate the problem, and just add, the S of 1 to I. This goes a step further, which is nice, easier to read, not really required. Okay, so we are trying to see if S1 to S of I can be reconstituted as a sequence of valid words. Good. All right, so what does our recurrence look like? So we're going to start with T of 0 equals true. A lot of students will ask, in this version, in a problem like this, is the empty set true or false? And it's not really well defined, right? Like, if I give you no words, no letters, is that a valid word or not? And you might say, well, without that information, I can't continue. What I like to tell students is that your base case is whatever you need to get your recurrence to work. So work backwards with that. Start with some number of characters and say, well, how would I figure it out for this number of characters? And as I work backwards, what does my base case need to be in order to set everything else in motion to be correct? So your base case may not actually be the first thing you figure out. You might actually figure out the rest of the recurrence and then work back and say, because my recurrence does this, I need my base case to do this. And so here, T of 0 equals true, not because it's well defined whether 0 characters is true or not, but because it's what we need for our recurrence to work. And that's it. So once we have that, our recurrence is saying T of I is equal to true if any, for any subset, T of j minus 1, okay, and dictionary of j of s, oops, to I, j to I, and then we go from j. We have j go from 1 to I, okay. And what this is saying is that we want to take any given window for I from 1 to n and j from 1 to I. So we're taking a given where we have this array, right? We are going to set our start of what we're looking at here, and then we're going to take I and we're going to move it through this array, and then for every single place where we put an I, we're going to put into j here some j, and we're going to test it. We're going to test, does the left half is the left half a sequence of words and the right half a sequence of words? If not, what about if we try j is right here? If not, what about if we try j is right here? So anywhere where we can place j such that the left half is a sequence word and the right half is a sequence of words, then this entire where I is trying to check, that entire section window can be made into a sequence of words. And if I can't find any j that can solve this, then for that window, it's false. Okay, and false is okay, right? Like if you had a word like right, if you had something like this and you were testing it, like if we were testing this window, the left side here is true, but the right side is not, right? And that's going to give you false. But one false does not end the entire check, right? The left side is true, the right side is also false. But the second I get to here, and I check that hello is a word and world is a word, I'm done. right? That actually works. We're good, right? And notice how the left side here, right, is checking to see if T of J minus I1 is true. And the second half is checking if the dictionary of that thing is true. And the reason for that is because while this part is solved, right, the T of J to I here, or T of, whatever order this is not something you can check. The only thing you can check to see is if the right side is actually a full word. And this works because no matter how many letters you check, right, the left side is a sequence of words, but the right side at the very end of it is a word itself. So you check the left side if it's a sequence of word, and you check the right side if it is a word, and that together tells you that the entire window is a sequence of words. So that's not what this is doing. And then at the with all that, the number of subproblems that you are keeping track of is one-dimensional, so it's O of n, right? You're only doing a T of I goes from 1 to n, which gives us an O of n number of subproblems. But for each I, you're checking from J for J, which is 1 to I. So this right here is O of n. This right here is O of n. So O of n subproblems, O of n squared runtime. Your final solution is T of n, because you want to know when the entire array is considered at the end here, if this entire array is can be reconstituted as a sequence of valid words. So your final solution is T of n, and then your runtime is T of 1, right? And there was a student that asked, well, if I know that the information is in at the end of the table, but the solution is probably also in the entire table, can I just always do a T of n return and look at the entire table? You can't in this case, right? If in this case I was saying, well, if any value inside my table is true, I then return true, that is not going to work. You absolutely, in this case, in this specific case, you have to look at the very final value to see if the final full-size array can be reconstituted to a series of words. So it's T. So you're extracting T of n, and your extraction is T of 1. So this is an example of a windowing problem that is O of n squared and not O of n cubed, which is what a student asked earlier. Any particular questions about this problem? Eduardo?
Yes. Can you hear me okay?
Mm-hmm.
Can you repeat one more time? Why is it TJ minus 1? I did not quite follow that part.
So at any given, oops, just happened. Sorry. So right here in hello world, right? If suppose this is J, right? And I want to know if all the letters before it could be reconstituted to a word, right? If this is J and everything I checked before that, this is J minus 1. So I'm checking from the where my array started all the way down to J minus 1. This right here is J minus 1. This right here is J, right? And so my dictionary check right here is J to I. And suppose, let's say like, my I is right here, and there's a whole bunch of other stuff down here that I'm not like really paying attention to right now. For now, I'm just working with this subset. I'm checking from J, which is this letter, down to I, which is this letter. Actually, this is probably better to, oops. It's actually the letter that you care about. So J, this is J, this is I. My dictionary check is from J to I, and then my check on the previous series of letters is from is at J of I minus 1. Okay.
Got it. Thanks.
Cool. Jafar?
First of all, thank you very much, because I thought that I have already visited this problem and I made it in a good way, but it happens that maybe I'm thinking about it in a very bad way. I don't know. I want to ask you because I know maybe it's a silly question, but I need to understand what I'm doing. So I thought about this problem in another way that we start from the first letter and we start doing appending the dictionary. So S of 0 will be, or T of 0 will be, sorry, T of 1 will be true if dictionary of 1 is true. But if it is false, then we append T of 2 to it, and then we start checking T1, 2. If it is true, then it is true. We correct that to 0, and we start the string from scratch. So it's like LCS. No, it's like a building 1D, and then it is O of n. And at the end, if everything is true, we return true. So I did not thought about it like windowing at all. I thought about it, it's like longest increasing substring, I think. String, yeah, substring. It's like I'm appending each time one element and checking. If it is true, that's it. That's great. I'm starting the string from scratch till it is true. If at the end I take false, that's it. It's false. The full data is false. But if at the end I take true, that's it. The full string is true.
Yeah, I can see approaching this as a somewhat LIS type problem where you're trying to find, like, longest string that creates a series of letters, and then at the end you're trying to find out. I mean, I think the setup is kind of the same. You still have to check, the TF J minus 1 and some, dictionary check, and then you just kind of keep track of that. I think the setup is basically the same, but I can see how you can look at this like it's kind of LIS like, which is okay. Like I said, like, sometimes you can look at a problem and it kind of fits multiple categories, and
yeah, but the runtime, in my opinion, is O of n. I see that you are trying to say that no, it is O of n squared because J may be everything, but no, it's only a string, like a space string that I'm memorizing.
You're welcome. You're welcome to post your solution in the practice. In the practice thread, and let students and TA take a look at it. I'd be very surprised if this was open. I am very doubtful this is open, because this isn't, even if this is an LIS setup, it's an O of n look back. You can't do an O of 1 look back because the previous letter being false tells you nothing about what this current letter could do to the full string, whether the full string is true or if the full string is false. You can't just look back at the very previous letter. What you have to do is
but you are memorizing from the last element that it is false. It is true. So whenever the true is finished, we start memorizing a string. And then you append to it, you append to it, you append to it, and then
but that doesn't work. And I'll tell you why.
Why?
Okay. So
let's take hello here, for example.
Yeah.
Hello, now it's true.
So this is true, right? Right here, you have
Yes.
true, right? Okay.
Yes.
Now this is false, right?
Yes.
Okay. So now either you have to consider L by itself, or you have to consider L with all the previous letters, right?
Yes, you are
Now,
true.
when I
So
add
this is
another
all
L,
square. Yeah, I understand. Yes, I
what is
understood.
this?
Understood.
Okay.
Thank you.
Yeah. You have to look
All
at all the
square.
previous letters because language works in funny ways.
Yeah. So
Right.
I need to go of n square. So here I will need a table instead of a string. Okay. Thank you very much. Yeah. Thank you. This was very helpful. Thank you.
Brianna, I'm gonna answer 2 more questions and then I gotta move on to the next one. So Brianna.
Okay, 2 questions. First, so the T of I true if any T of J minus 1 in dictionary as J to I. It's like saying, for example, is the current word can the current word that I'm checking right now against dictionary from J to I be reconstituted with the previous word that I already validated if it's true or false, because I'm checking
With the previous series
J
of letters. The
one,
previous
yeah.
series of letters. Yeah. So the previous series of letters have to make up words plus +1. Because what ends up happening, what you can do, right, is I need to another
Because I'm assuming T of J minus 1 already has a record of true or false based on what was checked before,
Yeah.
right? And it's like
Yeah.
saying, I'm just checking the previous subset of word has the current subset of letters, if it's a word, against what I already validated, if it's true or false.
Yeah.
Or false.
Yeah.
And the second question is, what will need to change on this problem to make it a big O of to the cube? Because I didn't understand what's the difference of how this k variable jumps into action and makes it a big O of
It doesn't in this. It does not in this problem, but there are different problems that are kind of similar in approach. Where instead of asking, like if instead of just saying true and false, like right, there's only a yes or no state for every single for all the smaller windows. If I'm asking you, okay, well, let's say it's Scrabble. Okay, not only do I want to know what whether I can make two full words with the Scrabble tiles I have, I also want to know what the most points are. So now that it's the most points, you can't just look at a true or false state. You have to you also have to look at the words and subdivide them into optimal words for Scrabble points. And at that case, you are introducing a k to check a valid true state for multiple possible better solutions. And that's how you could possibly turn this into O and cube problem. Can I make words? And if so, can I make optimal scoring with those words?
Okay, thank you very much.
Yep. Stefan?
Yeah, what's up, Steven? Yeah.
Okay.
So, okay, that's right. So basically, I was able to optimize my solution by basically, I don't know if this is allowed or not, but basically, I just stored all of the valid indexes where a solution was true, and then rather than iterating over the whole thing for J, I just iterated over the valid indexes, and that allowed me to like skip ones that are kind of obviously not correct. That kind of sped it up. Is that is that not allowed, or is that like, I don't know?
I would post your solution to the practice problem thread. I mean, like if there's like an obvious bug in it, I can live debug it. But like something like that sounds really complicated, and I would post it in the practice problem thread so people can look at it.
Yeah, I'm almost certain.
That's what the practice problem thread is for, by the way, is for you to present your answer and have everybody sort of chime in. So that is the best way to see if your answer would be correct or not.
Okay, but kind of what I'm asking is my question basically like I'm almost certain it's working because I did a lot of test cases, like almost 99% sure. But basically, I'm wondering, is this not allowed? Because would this sort of be something like memoization or something, or is this like I could post it, but I'm wondering.
Yeah, you could post it because I don't actually know what you mean. Like without looking at it, I don't know what you mean by that. So I think it would be best to post it.
All right, yeah, sure. Yeah, it's just storing the valid indexes where it works. But yeah, I'll show it. Thank you. Thank you.
Problem.
Yeah.
All right, I am going to move on to the next problem, which is longest common substring. Yeah, so I'm just gonna post this whole thing. So hopefully this problem isn't too bad. I believe the lectures did the longest common subsequence, and I also went over this as a problem type. So hopefully not too much as everyone here. Okay, so our subproblem definition is T of ij. We need a two-dimensional table because we're tracking every single possible comparison between the two arrays. And we are saying is the length of the longest common substring for x and y. Notice here, I don't actually have to define what the longest common substring is. If the definition of a solution or the definition of something is provided to you in the problem, you don't have to redefine it. You don't have to be like, a longest common substring means the following if it's already like implied in the problem. Ending with x of I equals y of j, which is 0 when the characters do not match. I don't think that's needed, but I like to let students know what's necessary and unnecessary. I feel like this right here is sort of unnecessary. Again, this is the same. It's a similar situation. What is it? What is the number when characters do not match? It actually can be whatever you need it to be in your base case, such that your recurrence works. So if it's undefined in the problem, like if the problem defines it, you have to absolutely match that. But if the problem doesn't define it, let your base case decide. The reason why we wanted to end in x of I and y of j is because we need to keep track of when a substring can no longer be continued. So if we don't force x of I equals y of j, we don't end up knowing when a substring can no longer continue. Okay, so that's why that exists. So with that in mind, your why did my okay? So our recurrence, right? So, and here I'll show you what I mean by working back from your recurrence. Okay, so we know already that if the two letters match, we want to add one to that previous best answer, right? The previous best answer might be also a match. And in the case, if the previous thing was a match and this thing is a match, then we have added one to that previous thing. If the previous thing wasn't a match, what happens? Well, we're going to add one to the reset. And how do we reset that? We have the second detail right here. If the two letters do not match, we reset it to 0. Thus, by adding 1 to it, we immediately restart the match substring. So what do we need in order for all of this to work? Let's look at our base cases. So generally, your I starts at 1 to n, right? And your j starts at 1 to n, right? So that's right here. Well, when I equals 1 and j equals 1, we end up with a this equation right here, right? So what if the first letters match? If the first letters match, this is actually 1 plus t of 0, 0. Okay? Right? Makes sense? If they match. So if they do, if they match, I need this t of 0, 0 to equal something such that a 1 match equals 1. We know what that means. If one letter from both strings match, it's 1. So if I go back to t of 0, 0, my base case then has to be 0 to add that 1 to. And that's how I determine what my base case is. Not because I have a deep understanding of what no matches mean. That just happens to be one of my base cases. So what else do I need for my base case? Well, let's see. What happens if I have I equals 1 and j equals 2? Right? Because I'm incrementing one at a time. I'm not incrementing both at the same time. So I could potentially get a match, and I want 1 plus t of 1 0. Oops, no, I said j equals 2. Right? Okay. And then what happens when j equals 3? Well, I could and I still equals 1, right? So I could potentially have 1 plus t of 0, 2, and then dot dot dot. I could have potentially 0, and right. I can not move my I, and as my j goes forward, every time it matches, I need to be able to look back at some base case for that. The same is true. Like right, if I set at every given point, my j is going to be equal to 1, and my I is going to go from 1 to n. So anytime I subtract 1 from I, when I when I look at this, sorry, if my j equals 2, and then this right here, I could potentially go all the way to 0 each time. So that's why I need this. For any I, as long as my j is 0, I want this to be 0. For any j, as long as my I is 0, I want this to be 0. That's how I get these base cases solved for me. And you see how this is going from 0 to n and from 1 to m? This is so that the two ranges doesn't overlap. Okay? Because t of 0, 0 is already set. If I set this to 0, this is again going to be t of 0, 0 equals 0. Now, this is perfectly good. This is great. This makes sure that you are not going to have a contradiction. That being said, because both of these are setting to 0, if this started as 0, it would also be okay. It's okay to start this from 0 only because there's no contradiction. Okay? If, however, for whatever reason, for a different problem, not this particular problem, for a different problem, if this wasn't set to 0 and this was set to like 1, I would not be able to set my range from 0 to m, because potentially this sets 0, 0 to 0, and this would set 0, 0 to 1. That's an example, not in this case, but just wanted you to be understand it. And then when we look at the number of subproblem, it is a this is O of n, this is O of m. Same here. Same here. So your table size is O of n times m. Your runtime is O of n times m. Same thing. And then your solution, because we are resetting to 0 whenever we break up the substring, our final answer is only going to be the longest common substring using those final 2 characters. The longest common substring may not use those final 2 characters. And because of that, I need to look at my entire table to see what the max is. And my entire table is n times m. Therefore, looking at that entire table is O of n times m. And so these are your implementation and analysis. Any questions regarding longest common substring? Lin Fen?
Thank you. So I think from my observation, the subprogram and recurrence, both of them are similar to the LCS, a longer common subsequence. So can you tell me what's the difference between this one and that one? Like, is that because the extracted difference? So where are the difference located between these two? This one.
The longest common subsequence is, I believe, covered in the lectures, right? So yeah. I would definitely take a look at that and compare the 2 answers. There's the most obvious thing is that this 0 right here that gets reset, this second line right here is not the same as the longest common subsequence. It is different. So understand what the difference between why this gets reset to 0 and why it does not it gets set to something else. If you want to later on watch the recording, I go over the difference between the 2 problems earlier in the office hours. So hopefully that'll help. But definitely watch the lectures and see what the difference between the solutions are. It is extracted differently, but that is not the main difference.
Okay, thank you.
Yep. All right. Brianna?
Thank you. So the way I usually go about base cases is if by asking questions like, for example, T of 0 is because I don't have a string for y, or I don't have a string for x, right? So I usually go, if I'm trying to calculate the longest, then I have nothing to sum if I is not present or j is not present. That's the way I usually go about base cases. But you also said previously that sometimes your base case is whatever you need for your recurrence to work. In this particular case, I understand why it's 0 because we have nothing to show, but I didn't understand why you had to run the analysis of the one on the green part below 1 plus t of 0, 1. I didn't understand that part.
Analysis.
Which part? And the corner, bottom corner to the right. 1 plus t of 0, 1, 1 plus t of 0, 2. I didn't understand that analysis.
This part right here? This is not an analysis. This is me running through the algorithm.
Okay. Okay, thank you. Sorry, and a follow-up on the question I asked. Is that a bad approach, setting up base cases just by asking if I don't have I, but if I don't have a X, anything for the X string, but I do have for Y, then I still have nothing to compare to, so it's okay to say 0. Is that a bad approach?
You can do your base cases whatever makes sense to you. I know that sounds like a cop-out answer, but it's honestly the way I look at it. You can either decide, okay, I understand what base cases mean, and I want to set up my base case to influence how I set up my recurrence. Or you can say, I'm going to start at an arbitrary I and j. What information do I need for I and for t of I to set t of ij? I need to look back at my subproblem. Okay, well, if I look back at my subproblem and I keep going back far enough, at some point I have to stop. When I stop, what do I need that base case to be in order for me to have a correct recurrence? And that is just how I set my base case. Either approach is fine, whichever feels either more intuitive. And it can even change depending on the problem. Some problems might be, oh, the base case is super obvious, so I'll use that as a stepping stone to building my recurrence. Some problems might be, yeah, I don't really know what the base case should mean because it really doesn't have an assigned meaning. Let me start with the recurrence, and whatever I end up with my base case, that's what I'm going to do. For example, the Fibonacci problem that you get, the base case is defined, right? You know what the Fibonacci sequence starts with. That is a defined base case. Start with that. In this particular problem, I don't really know what T of 0, 0 means logically until I kind of have to use it. And if I have to use it, I want it to be 0. That's why I set it to 0. Could also be intuitive to certain students, and that's fine.
Thank you.
Yep. I'm going to answer one more question, and then I'm going to move on. Karishma?
Hi, can you hear me?
Yes.
So I know you already went over it probably a few times at this point, but just to clarify, the base cases where you have one is less than or equal to j, less than or equal to m, why can we not say, or why did you choose the approach of doing that instead of saying t from 0? Because 0, 0 is going to be equaling to 0 as well. Based off of when you went through the walkthrough of it. So why?
Yeah. So why do I go from 1 here?
Yeah.
Okay. Your recurrence has to come after your base case. If your recurrence includes your base case, suddenly your base case has no base case to it, right? So let's say we start with 0, 0, right? So if I start with 0, 0, when I'm calculating this value right here, I'm suddenly calculating t of -1, -1, right? Because I need this value in order to figure out what my vector. If this is 0 and this is 0, t of 0, 0 is equal to 1 plus t of 0 minus 1, 0 minus 1, which is t of -1 minus 1. Now I need another base case for my 0, 0. So then if you set that, and then you start this from -1, now I need t of -2, -2. So your base case should never be part of your recurrence, because one, you possibly could assign a conflicting value because you've already assigned the base case to something, and now you might assign that to something else. And two, your base case is what powers your recurrence. So if your base case is included in your recurrence, what's going to push that? What's going to be the base case to that? And that's just not going to work.
Right. No, so I understand that, but I guess I'm talking about the second base case where you're saying that for j is 1 to m, why j would be from 0 to m in that case, because that's your base case, right? Those
I
two.
already explained it. I explained that you can do it from 0 to m. That's fine.
Oh, okay, cool.
Yeah. But it also just works from 1 to m too. That's fine too.
Okay, sorry I missed that. Thank you.
Yep, no problem. So a student in chat that caught my attention asked, setting something twice is trivial in runtime, which is true. It is an all one solution operation, very true. Why is it such a big deal in this class? It seems pedantic in this example. Resetting values in recurrence is not, and we just applied this rule for everything. So, I don't know if you're asking like, why don't we allow you to reassign a variable over and over again? Does that really matter? And I think the answer is that, like,
Oh, sorry, I asked this question.
Oh, okay.
Yeah, Tim answered it. So, like, in the case of like our base case here, that Krishna just asked as well, like you just mentioned that it's okay in this case. But in the recurrence, I can see how, like, if we're resetting the value, then like a recurrence is probably not accurate. So there's a distinction there.
Yeah. So as long as your setting of your values are not contradictory, you can do that. That's okay. You also don't have to do that. So that's okay. So yeah, that's what I was covering. I know it's like it's like a complicated, like, little subtle thing to it, but that's just the way it works out. Okay.
Thank you.
All right. Yep, no problem. Next problem. So next one is making change and making change k. Okay, so the problem asks, consider the following variation of the change-making problem 6.17. You are given denominations x1 to xn, and you want to make change for value v, but you are allowed to use each denomination at most once. For instance, the denominations are 1, 5, 10, 20. Then you can make change for 16, which is 1 plus 13, and for 31, which is 1 plus 10 plus 20, but not for 40 because you can't use 20 twice. Okay, so this is a knapsack problem, and you are reusing not able to reuse the value. This looks like knapsack, which it does. But the other thing this is it's actually called subset sum. So the subset sum problem asks, given a bunch of values, can you add up to a certain value? Which in this case, can you take a bunch of coin denominations and add up to a change you are trying to get? Subset sum and knapsack problems are very related in that with knapsack having both a value and a budget, a subset problem, or in this case, the coin change problem, is basically saying a single denomination represents both the value and the budget. It is a 1-to-1 ratio, so you want to get the highest value possible, but still be able to fit that same value into your thing. And in this case, you're just asking, basically, the highest value I can get with all my coins within a certain budget, is it equal to that budget, which is equal to the change I'm trying to get? There's two ways to solve this problem. You can either solve it as a maximization of your value to the budget and then saying, does my value match the budget that I have? Or you can do a true false check to say, can I make change for a certain value? And if yes, then adding more and more change to it, can I make subsequent values with the change? The reason why you approach 6.18 with the maximization value approach is because that same approach is very, very useful for 6.19, which we will also show. When I solved this problem, I initially did a true-false table. But when I saw how 6.19 was presented, I ended up going back to it and using a maximum value table, which allows me to easily modify that to be 6.19. And so I'll show both, and then we'll talk about how that transforms to a 6.19 solution. So this is the solution to 6.18 using the maximum value. So your T of ij is the maximum sum at most j using a subset of coins x1, x2, xi. This shows a few things that we should be aware of. One, your subproblem definition, while it is usually a rewording of your problem definition based on a subset of problems, it doesn't have to be. It's allowed that your subproblem definition be different from your problem statement, as long as you end up using that subproblem definition to solve what the actual problem is asking. So in this case, the two things are matched up because it's actually one approach that you can use it to solve this problem. So while I say it's generally a good idea to use the same problem statement, you don't have to. The second thing is that when we are considering a subset of the coins, because we can't repeat, J here is used to track some value you are trying to get to, and I is tracked on the coins of 1 to I coins. You're not using every coin possible at that table entry. You're using a subset of coins, and so you have to indicate both parts. Anytime you have a value here in your table, I and j, you have to bind the input to it such that j and I is declared. What do you need that I and j for in your subproblem definition? Okay. Then once we have that, our recurrence again, we could just start with this part right here and then work our way back to the base case. Which is what I typically like to do in these type of problems, because I don't I mean, yeah, you can reason it out. You can say no matter how many coins I have, if I'm trying to make a value of 0, then I have 0. Then my maximum value is 0. That makes sense. And then no matter what value I'm trying to make, if I have 0 coins to consider, the maximum value I can use is 0. That also makes sense. So in this case, you can just use the logic out. And notice here, how again, this is starting at 0, and this is starting at 1. And once again, you could start this at 0 if you really wanted to, because the two actually set the same thing. So there wouldn't be a conflict if you start at 0 on both, and you don't have to. And then your recurrence is your I and j is equal to the max of I minus 1, which is what happens before this denomination is considered for this particular value. So take my previous best solution and compare it to if I remove enough room of my value for the weight of this coin, and I add the value of this coin to that previous best value. What's interesting here is that instead of doing a value of I and a weight of I, they're the same thing. They're both indicated by the denomination of the coin. So it's x of I and x of I in both spots. Normal knapsack would just be V of I, B of I, W of I. But here they're the same thing. The weight and value is the same thing. Again, if x of I is less than or equal to j, otherwise it's just going to be the T of I minus 1j. Now, these two things can be written a little bit differently. You can say if x of I is less than or equal to j, and then if x of I is greater than j, this also could just be replaced with the word otherwise, because if it doesn't fit this particular if statement, then everything else is what you're looking for. The main important thing is that if you set up your statement like this, where you have a if and then a second line, they have to be complete. It has to fit all cases. So a if less than or equal to j, if greater than j is the only two possible result of the test. That's okay. Or you can do if less than or equal to j, and this is otherwise. That's also okay. What you cannot do, because you end up with a unknown state, is right? In this case, what happens when x of I equals exactly j, right? You have a unknown assignment, and you're going to lose points for that. Okay. And then from there, this looks exactly like knapsack, because it is exactly knapsack. You're just trying to fit as much as you can into your bag or bucket or whatever until you can't anymore. And what you're really asking, though, is a little bit different than what the table entry is, but we'll get to that. The number of subproblem is O of n times v, right? When you want to consider this, all you're looking at is how you declared your table. Your table is 2 dimensions. The first I is bounded to n number of coins, and your j is bounded to sorry, let me take that back. No, yeah, that's right. I is bounded to your number of coins. J is bounded to the number of values you are considering. So it's n times v. That's the number of subproblems. When you go to fill out your table, you have this is O of n. This is O of v. And then you look here. What is your recurrence? Your recurrence is a if statement, do a max between 2 calculations, else set it to a previous lookup, which is O of 1. So this is an O of 1 step. This is an O of 1 step between the two. So then, oops. No. I always forget to lock the. Make this a little easier to read, hopefully. O of v, right? So then it's O of n times O of v times O of 1. So that gives you that answer, O of n times v. Okay. What is the return that is extracted? It's not just the value at nv, right? Because that tells you what the maximum value is, but that's not what the question is asking. The question isn't asking you what is the closest you can get to the change that you're trying to make. The question is, can you make that change? And so you return true if the value is equal to the maximum value you can make at that with all the coins considered for that value. If it matches, then it's true. Otherwise, you can't make the change for that value and then return false. And this is a O of 1 lookup because it is you're just comparing the final value in your table to the value that you already have. Okay. Questions about this particular problem, Bradley?
Yeah, you had mentioned that sometimes reducing a problem to another problem is okay, and sometimes it's not. Can you kind of expand on why that's okay in this instance, and some instances maybe that's not okay?
You can always use some problem that you some problem approach that you have and just do it. Like right here, if I give you this solution, you don't need to know what knapsack is or what the knapsack solution looks like in order to say program this solution, right? Like your previous knowledge of knapsack doesn't really matter. When we say a reduction in the problem and I go, oh, I can reduce this to knapsack, and if I reduce this to knapsack, I can solve it this way. Now you have to understand what knapsack is. You have to say, okay, well, knapsack sets it up this way, and I've reduced this problem to knapsack, and therefore here's the things that I have to map to the knapsack problem. We don't allow that in dynamic programming.
I see.
In dynamic programming, your solution has to stand on its own. Later on, when we move to say graphs and NP complete, you get to a situation where you're like, oh, this problem is really just looking for the minimum spanning tree. This problem is really just looking for the shortest path. And by setting these things up, I find the shortest path, and therefore that's my solution. Now you're allowed to do that reduction. Here we don't do that.
I see. So okay, yeah, because I don't know. This is just my past experience, but it's like, yeah, if you can just literally say, hey, reduce to here, and then the runtime is the runtime of knapsack, but we can't do that for up to a later point. It sounds like so. Okay, thank you.
Yeah. Your solution has to be, when I read your solution, I shouldn't have to know how knapsack works in order to know how you're solving the problem.
Thanks.
Garrett?
Hi. So we've seen this a few times where we have cases, perhaps, where we have if else or if otherwise. Are there problems where we may have 3 different cases, or is that maybe where, like, if we identify 3 cases, we might need to rethink the problem?
I can see some problems that have 3 cases. In fact, let me see something.
It's maybe on the rare side, though.
I wouldn't say it's on the rare side. It's also like, so I think there's situations where something is required to be done that way and something can be done that way, right? So I do think that it's probably rare for a like a 3-statement type of thing deal. But you can always do it that way if you force it enough, right? Like right now I have less than equal to j and greater than j. I could easily remove the less than equal to j and add an entry for equal to j and give you the exact same statement, and it would still be valid. It's a 3-statement line and it still works. But I can also combine the two, right? Like you can do it that way. I think there are certain problems that would need all 3. Would need more than 2, but I can't think of any off the top of my head.
Right. So we can kind of like work through our table and fill it and still be within the optimal runtime, then that's fine.
Yep. I have started to learn that Dr. Brittle is really good at surprising students, but also equally good at surprising TAs. I have run into a few times where I said, oh yeah, this will not happen or this will never happen, and then get caught off guard by Dr. Brittle. So I've tried to be a little bit more reserved about it.
That sounds like an intimidating statement.
Yeah, I guess. I mean, that's why, and I think it's a good thing, right? Don't train yourself to be like, you want to optimize your strategy to sort of fit most patterns, but you don't want to be so focused on it. Sorry, it's a angle. You don't want to be so focused on it that you don't allow yourself to expand beyond that scope. So that's best I can do. All right, we're going to move on to 6.19, which is very similar to this problem. Oh wait, sorry. I promised I would quickly and hopefully I stayed true to that, go over the alternate solution and then explain why that works. So instead of doing this check at the end, right, we could also just as easily encode it into the actual solution. So this is the note on your practice solutions that there's an alternate form. So d of ij is true if there's a subset of coins 1 to I to form the value j. So this is very much your problem statement reworded as a subproblem. And then your base case is d of 0, 0 equals true, and then 0 of j is equal to false for any j up to that value. So if I am trying to make j value from 1 on, right? No matter what, if I have no coins, I can't possibly make that value. Now notice here how I said that, occasionally you end up with a 0 that you can use a 0 or use the 1 and it doesn't matter. In this particular case, it does matter. If I was to show this as 0, I am going to have a contradiction. What ends up happening is that when this is set to d of 0, 0, I'm going to say this equals false, which immediately contradicts that 0, 0 is equal to true. So it doesn't always work, which is why you need to be careful, understand what you're doing, and not just, try to come up with a hard and fast rule that this is always going to be the case, okay? Okay. Then your recurrence is d of I minus 1, d of ij is equal to d of I minus 1j, which means if I don't have this coin, if I wasn't considering this coin, could I make this value? If I can make this value without this coin, then I certainly can make this value with this coin, right? Makes sense? Or if I couldn't make the value without this coin, can I now make this value with the coin, which is d of I minus 1, which is, before this coin was considered, and j minus this denomination. What does this mean? It means that if I want to know, can I make change for 75 and my x of I equals 25, it is sufficient to know if I can make change for d of I minus 1, which is before this coin was considered, and 50, right? Think about it. If I had a quarter left, and I want to know if I can make change for 75 cents, if I didn't use this quarter already, can I make change for 50 cents? If I can make change with 50 cents with all the other coins before this quarter was considered, add a quarter to it, bam, I can make change for 75 cents, right? So that's what that line means. And if this coin is too big for the value I'm trying to make, then all I need to know is if I could make the change for this value before this coin was considered. Do the same thing with your where loop, and then your return value is d of nv, which is because you are carrying the true false all the way down. All you need to know is if the final value with all coins considered can be made change, and so that's an O1 return. This one doesn't have the analysis, but you should be able to figure that out based on the recurrence. Okay. Ooh. Okay. But Lamfin?
Back to this answer, alternative answer. I want to know where the xi located for the second one. You said the dij, the recurrence, equal to di minus 1 j or di minus 1 j minus xi. So because in the original lecture, I think the xi should be somewhere in the second part as well, right?
Your xi is because you're not trying to optimize anything, you're not trying to add value. So you don't need it for value purposes like you do with the original problem. It's just there to get a true and false decision. So I don't need to know what the what the best value is. All I need to know is was the previous was a different change amount or different value amount something I can make change for. Like I said, if I can make change for 50 and now I have a quarter, I immediately can make change for 75 cents. Does it really matter if I can make change for 74 cents or 73 cents? No, right? I don't need to track that value anymore. So I'm not adding 25 cents to anything. I'm just saying yes or no.
Okay,
that's what the
thank you.
variation between the two is.
Thank you.
Yep. All right, and this allows us to solve 6.19. Okay, 6.99 asks, here's another variation of the change-making problem. Given an unlimited supply of coins in denominations x1 to xn, we wish to make change for the value v using at most k coins. That is, we wish to find a set of less than equal to k coins whose total value is v. This might not be possible. For instance, if the denominations are 5, 10, and 6, then we can make change for 55, but not for 65, given the efficient algorithm for the following problem. So what you end up seeing is that you have 6 coins, right? So in order to make 55, I can have 5 10s and a 5. That's 5 coins, and I can make 55. In order to make 65, I need 6 10s and a 5. That's 7 coins, which is not enough, right? That's too many coins to do k. So the input is similar, and there is a possible make change for v using most k coins possible. So let's see. Okay. So in order to do this, what we're going to do is we are going to track how, not just can we make change for this value, but how many coins do I need, minimum number of coins I need to make change for this value. Okay. I think we're not a sync. 1 second. We get this. I think my thing crashed. Okay, fixed it. Sorry. All right, so we're going to say that T of J, and remember, you don't need to track the I coins because we have a multi-set. We can use unlimited versions of this coin, so we don't need to track which coin we're currently considering. Doesn't matter in this. So you could do this with a two-dimensional table if you want. For this one particularly, we're going with a one-dimensional table. This is considered the simplified version, I guess. So T of J is equal to the minimum number of coins needed to make the exact value J using a multi-set of coins, x of 1 to x of n if possible, or infinity otherwise. Now, you might be asking, hey, didn't you say that we must use a subset of the input and not the full input? And why am I allowed to use x of n here? Because the x part, the coins, is not tracked in our table. Our table does not have an entry for our coins. And therefore, I don't have to use a subset of coins because I want to say I'm just going to consider all the coins all at once and then code it into T of J. my number of coins used, or the coins I use for T of j, is not a subset of coins. It's considering the entire set of coins. Okay, and that's the key reason why I can do x of 1 all the way to x of n here. So we're going to state the recurrence in how this works. So T of 0 is 0, which means that the number of coins I need to make 0 is 0 coins. That makes sense, but we could have worked our way from the recurrence to the base case if we needed. Now, we are going to say that we're going to set things to infinity otherwise. That tells us that if I can't make change for this coin, I want to be able to track that I'm not able to make change for this value. And so one way to do it is to set it to infinity. One way to do it is to -1. Whatever you have that indicates this is fine. Infinity is just easier because we can take a min-max off of infinity, and it's just convenient. So what I'm going to say is that, okay, well, if I have a coin, if I go from 1 to n, so I'm going to consider every single coin, okay? And I'm going to take the minimum of my one coin, the coin I'm considering, and I'm going to check all other, all the previous values that I am making change for, okay? So let's say we have, 10 and 5, okay? And the value we are trying to get is, okay? And so this is a good example because it's already in things. So if I was to look at the coin for 10 and I go, okay, well, what is the minimum of 1 plus t of 55 minus 10, right? Which is equal to 1 plus t of 45, okay? And I'm going to compare that with the other coin that I have, which is 5. So it's going to be 1 plus t of 55 minus 5, which equals 1 plus t of 50. Okay. And I'm going to keep track of that. I'm going to add 1. The reason I add 1 is because when I want to consider this coin, I add it to the previous value that I made change for. So just like, if I took 3 quarters, if I took 2 quarters to make 50, and I want to know if adding a quarter can make 75, I check t of 50, which is 2, add 1 coin to it, which is 3. Now t of 75 is 3 because it takes 3 coins to make 75, right? So this is a similar intuition idea. So we can just pretend we already solved for the other one. 45, I believe, would be 4 10s and a 5. So this would be 1 plus 5, right? T of 45, we said, 4 10s and a 5. And then this right here is also actually equal to 1 plus 5 because it takes 5 10s. Okay. So the max of that would be, it would take me exactly 6 coins to make right. And it doesn't matter which combination I use. It works. So now I know that the minimum number of coins to make 55 would be 6. Okay. And as I keep tracking that, now my question at the end is, what am I looking for? Well, if my target value was 55 and my k equals to 6, I'm asking, is the t of 55 less than equal to the 6 that I assigned? And if I can't, then it's true. Otherwise, it's false. And so this is there's all of these subproblems because I have one dimension that I'm keeping track of, right? I'm keeping track of j here as one single dimension, so it's all v. This j, right, is across v, so this is all v, right? But within each t of j, which is across v, I am doing n work, right? Because right here I'm going from 1 to n, so this is all of n here. This is all of v here. That combined gives me this all of v times n work. This all of v table number of subproblems. And then this is my extraction, which I already explained. And this is an all of 1 because getting one single value and comparing it to a known value is all of 1 operation. Okay. Any questions on this particular problem? Mahitam?
Hello, can you hear me? Can
Yes.
you hear me? Okay.
Yes.
Okay. So can we take out the one outside of the min? Why included within the min? Is it okay to take it out? Would be fine.
Can we take out the one? Yeah, I mean, you can take out the one and then add it to the min of whatever you find. That's fine.
Okay, got it. Thank you.
You have to add it. You have to add it because that is the you adding that coin. But you can do 1 plus the min of all of that. That's fine.
Got it. Okay, yeah, that was my question. If I know I had to add it, I just don't know if that was required to be inside the min. Got it.
Yep.
Thank you.
Yep. All right. Minjanatha.
Hey, hi, Joves. I think I'm following this solution, but I'm a little lost on how the table T would look like. Is it similar to the knapsack where you start from 1 all the way through V, or it is just a... Oh, okay.
It's similar. Student is asking, could 6.19 be done using TF table? Also, I don't believe so. The reason is, what is your true false representing? If your true false is, the obvious thing would be true false. Can I make change for this value with k or less coins? Then when you go to add more coins to it for more values, how do you derive how many coins was used on that previous value using the true false? The true false loses the information that you would need to know if you can make the current value using less than or equal to 6 coins.
Joves, I think I do have an implementation that works with the true false table.
Okay. Do you keep track separately how many coins used to make that?
I only do it over B or over the value. So I have like whether or not an unlimited supply of denominations can make change for V with at most I don't know what I wrote there, K coins.
Right.
Or most, yeah. And then you do an OR over any coins that are less than the current capacity for all values of I from 1 to n.
What do you mean less than the current capacity?
Well, because it's I only have a 1D table with the
right.
So if x at I is less than or equal to B or the current capacity,
right.
You do that for all values of I from 1 to n.
Yep.
And if the t at B minus x of I is true for any of those values, then you know that you can add. Then you know that it's true for this value as well.
So the problem with that is that if I have, let's just make up a number, right? T of 55 equals true, right? And then T of 60 with x of I equals 5, right? So T of 55 is true, so this is also true, right? Is that what you're saying? If you're saying something here. Okay, anyways, so if this is true, how do you know how many coins this took and whether you can add 1 more coin to it? Like if this took 6 coins, how would you know that this should be false? Because 1 more coin to that 6 coin now puts you over K. How would you know this is false?
Oh, I see. I actually, I messed up in writing my solution because I didn't take into account K anywhere. Whoops.
Oh, that's a very important part of this problem.
Yeah.
So yes, you need to. Yeah.
Well, I wrote it in my
so
subproblem and then didn't consider it when I was writing my recurrence. Whoops. Okay. Yeah.
Without K, it's 6.17, right? This is 6.7 if K is not considered. Then yes, you could do that with the tree table. You absolutely can. But when you need to track how many coins are being used to make each of those, you have to you cannot use true false.
Wow.
And this is actually why we
Good point.
do 6.18 and 6.17 using the values instead of using true false, because if you were to do 6.17 using true false and you do 6.18 using true false, that's fine. Once you get to 6.19, you realize, oh, true false loses the precision of what I am trying to track in order to solve it. And so then you kind of go back and go, okay, 6.98, I want to track values, 6.17 on track values. Yep. Okay, Alejandro?
Hey, Joves. My question is, like now that I'm looking at it, it makes sense, all good, but honestly, I wouldn't have been able to come up with it myself. I wanted to ask, for some tips on looking at this knapsack type of problems on how to differentiate whether you need to iterate over your weight or your value. Because looking in hindsight, for example, we are iterating over the value because the k itself is the goal of the problem, right? We just need to answer true or false. Can we make change for a given k? And in the return, we just iterate over all of the possible values. But the way that I was going, right, I was trying to iterate over the k in my table. As in, the maximum change that I could give with k coins, right?
Yeah.
So just wanted to ask for strategy, look at these problems.
So two things. Your weight in this problem that's similar to knapsack is actually your value, right? Your value represents both your V here represents both the value and the weight, right? That's how this breaks down. The K is sort of a brand new variable that doesn't add, that isn't what the original knapsack problem does. So it's not, you hopefully recognize that. The second thing is, and I think this is a general advice to all the students watching this. If you look at this problem and you go, oh my God, if this showed up on the exam, I would never be able to solve it. And that's fair. That's absolutely fair. If you looked at this problem presented to you for the first time on the exam, I would not expect you to be able to solve this. And Dr. Berger shouldn't either. The understanding for this class is that every time you see a problem or some variation of a problem, you learn from it. And then the exam is tailored to be fair based on the information and the problem set that we have you practice. This problem, as a first time, as a homework, as a practice, as an exam, is unfair. This problem, or a very similar variation to this problem on the exam, would now be fair because we've taught you how to solve this problem. So don't worry about it if you solve this problem and go, oh, I couldn't get the intuition for this. If you had the intuition for every single problem we've ever presented to you, there'd be no reason for you to take this class. You've already been able to solve all these problems. The idea is that you tried this, you now understand how to solve this exact variation, and then if I tweaked a little something, you should be able to, using the understanding that you've learned here, apply it to the new problem. Hope that helps.
That makes sense. Given that the coin change is such a popular problem and so many variations, if I wanted to create one for myself, do you think that having to return the coins needed to make the change would be a good variation to practice or to challenge oneself within the context of the class?
Returning the coins needed to make this would just be a backtracking problem, which you're welcome to do, and I'm sure that's a good exercise to understand. But I don't think you would particularly see that on the exam because we like I said, we try not to give you
no backtracking.
Yeah.
Okay. Fair. Thank you.
All right. I'm gonna answer a couple more questions and then try to move on. Minjanatha?
Joes, I solved this like a regular knapsack problem, like a knapsack table on the table, and then there was a second table to track the number of coins. I mean, is that a valid solution, or did I miss something when I was?
It's a valid approach. I would post it in the practice thread so that other students can take a look at it. Yeah, I think there is a solution that can be done in.
Thanks.
Because you're basically just tossing out one table and using the second table. Like you're using the first table to help you get information about the second table. This is just basically saying, okay, well, if you're having both tables, I could just do everything in just one table and it's fine. But if you need two tables to get the information and then you return the right answer from the right table, that's fine. It doesn't add to the work or anything. Blake?
Hey there, can you hear me okay?
Yes.
Awesome. So for the previous version of this, using the truth table, we didn't require a certain subset of coin denominations. We just said if it was possible to make the precursor to some certain value, that we can get that value back. So how do we know? Because the question for doing this with the truth table is how do we know we had 5 coins or X amount of coins such that we could add one more to it? Can't we just encode that information in a hidden way like we did previously? Because like if the other one can rely on us not knowing the denomination of coins, wouldn't it be sufficient just to say like at each step it's the minimum possible number of coins?
Yeah, that's what this answer is, right? You're the minimum right here, the minimum
But in a
number of
truth
coins.
table sort of form, like instead of returning the actual minimum, just like saying it's true if it returns some minimum value of coins.
Right, but so I went over why that can't happen, because you need the information of what the previous value used as its minimum number of coins so that you can add one to it, right? Like I said, like if T of 55 is true for 6 coins, how do you know that T of 60 is false without knowing how many coins it took to make T of 55?
Totally. Yeah, I follow that part. So then my confusion is on the previous one. If we don't know the coin denominations, how can we make that
Because the
claim?
previous one didn't have that requirement. The previous one didn't say you can only use so many coins. So all I cared about in the previous one was, can I make change? Yes, then I can also make change if I add a coin to it, right? Like I don't need to track how many coins there are. That's why this variant is different.
But you need to know the denomination of the coin to know if you could make
on
change.
the previous one.
Yeah.
On the previous one.
Yeah, like if you had like you're an example where you had 75 and you subtract 25.
Yeah.
You would need to know your coin had a value of, you have a coin in your set of 25. But here we don't. They could have any values.
We encode in here this I on which coin we have considered. So we never want to double consider this coin. That's why this D of I minus 1 is saying before this coin was considered, what could we get? So this is the very key important difference between unlimited and limited instances. An unlimited instance, which is 6.19, is slightly different. We don't care. We don't keep track of I. Sorry. It's confusing. We don't keep track of I in this table because we don't care. Here, we absolutely need to know what happened before this coin was considered. And that's why we're I minus 1. Okay. Hopefully that helps.
Awesome, thank you.
Yep. We are going to try to get past the last 2 problems. Hopefully, totally understand if you are tired and you need to log off, and then you can just kind of watch the recording. I absolutely hate this problem. This is one of my least favorite problems. I won't even call it favorite. I'm trying to get this problem banned for like the last few semesters. Okay. The issue I have with this problem is that in itself, it is one of the more difficult problems we have because it is a chain matrix multiplication problem. But that's not where the hard part is. Understanding this problem is so frustrating that I just don't know why we have this problem. I bet many of you who attempted this problem, right? It wasn't like you were trying 4 hours or however many hours it took you to understand how to apply the windowing technique to this. You were just trying to figure out what this problem was even asking you. And every semester, I forget what it actually is asking. Okay. So the idea is that every single question has a certain percentage of how often that word is searched for. So begin has a 5% chance to be searched for, do 40%, else 8%, so forth and so forth. So I think the total here is 100%, if I'm correct. Looks about it, right? So these are the only words you can search for, and together they offer 100%, right? So that's one thing. We want to organize them in a binary search tree. So a binary search tree means that they're alphabetical, right? Well, binary search tree means you are them sorted in some way. So in this case, they are going to be alphabetical. So the keyword in the root is alphabetically bigger than all the words in the left subtree and smaller than all keywords in the right subtree. So yeah, it's an alphabetical order. Figure 6.12 has a nicely balanced example on the left. In this case, when a keyword is being looked up, the number of comparisons needed is at most 3. For instance, in finding while, only 3 nodes and then and while get examined. So, oops. Is being looked up. So you start off by looking at this letter. So you're looking for the word while, right? So you start off by looking here. And then you go, is my word to the left or to the right of end? Well, it's to the right, right? So then I'm going to look at then, and I'm going to say, is my word to the left or right of then? Then it's while. This is how binary search works. And on a nice balanced search tree, when everything has the same chance of being searched, you want a balanced search tree. You want as few levels as possible so that there's an optimal solution. No matter what word you're looking for, you have to go at most 3 levels in this binary search tree, right? But this isn't optimal if you're presented with frequency, okay? Because frequency changes how often you look to the left and right. Suppose that begin is something I look for constantly, and while is a word I never look up. This balanced search tree is going to give you 3 levels to the word begin and 3 levels to the word begin while, but it's not optimal if I'm always looking for this. Every time I want to look for this word, I have to go 3 levels, even if I never look up this word. So the idea is, if the word begin or some words, right? This word do is looked up very frequently, right? In this case, I have a cost of 1 level to look up do. In this case, I have cost of this is cost of 2. This is cost of 1 to look up do. So this one is more optimal for this particular word. With that in mind, we want to rebalance our tree such that we get the lowest average number of comparison based on the frequency that we have. Okay. So by this measure, the best search tree is the one on the right, which is the cost of 2.18. Now, how is this 2.18 calculated? Is the key to how our solution is. So let's look at that. Okay, that should give you everything. And then I always mess up looking at this. Let's figure out this is calculated. Okay. The way this is calculated is really unintuitive. The question is, how often am I going to look up this letter end? Okay, it's going to be 4% frequency times 1. The reason why it's times 1 is that I will only ever look up the word. I will only ever traverse the word end when I am looking up exactly 1 word. Okay, that's the only reason I would ever hit that level. Okay, and then the next one is 2, which is what letter is that? 0.4 and 0.1, which is do and Gotcha. I always get this confused.
Is the equation of the cost for the diagram on the left? I think it's on the left diagram, not the one on the right.
Oh, is that what? Okay. Okay, that's why. Okay, cool. Thank you. That helps a lot. Oops. All right. All right, let's try this again. All right. And is all right, 0.4. Okay. So this is a one level of check. If I wanted to look at this, right? So that's 0 times 0.4. Okay. If I want to get to the second level, my the chances of me going to the second level, the chance of me looking up two words to find what I'm looking for is 0.4, which is do, plus 0.1, which is then, right? Okay, so this is the average time I'm doing two levels of checks is 0.4 plus 0.1. Okay. The average time I'm taking to do three levels to check, which is this bottom tier. How often do I go all the way down here? Well, it's going to be 3 times all of these individual letters, which is 0.05. I mean, words, which is 0.05 plus 0.08 plus 0.1 plus 0.23. Okay, those are my levels. I'm not going to bother calculating this, but I think it would be cool if you guys calculated this. Yeah. Okay. 2.18. I mean, I guess I can start it. So do would be 40%. So it's 1 times 0.4 plus 2 times begin is 5%, while is 23%. Right. And then if is 10%. Else and then is 8.8 plus 0.1 and then 5 times n, which is 104. Okay. So that should give you 2.18, hopefully, if I did that correctly. Feel free to double check that if you want. Okay, so what we're trying to do is subdivide up our words into this into an optimal average. Okay. So with that equation in mind, our solution looks like this. The T of ij equals the minimum cost to look up the words from I plus 1 all the way to j. Okay. So on any given ij, I want to know what the optimal way to balance it is. Okay. Well, what is the optimal way to balance it? So first, we're going to sum up the probabilities of I to j. Okay. So that is the cost of the probabilities of that level. And then we're going to add it to the minimum of T of I up to k minus 1 and T of k plus 1 to j for all wherever we try to break it up. Okay, so I'm going to take my subtree. I'm going to just go to the left side and go say, what's the best way to break up the left side? What's the best way to break up the right side? And then the middle. When you look at the sum, so if you look at this T of I right here, that is the cost of this one particular word, right? So the cost or the probability of while is itself, right? So this last word, if this is T of NN, then this is P of N, which is that what's the last word on the list? Is while, yeah. Okay, and then so forth for every single intermediate word, that is its probability. Okay. And then what this sum does is that at every single level that we are calculating this, as every time we move up and up more, this sum right here which is the probability right here, is added again, right? Because you see how this 3 times this? The very first time this is calculated is equal to this 1 time. But then when I expand the window, these encode all the layers below it. So when this layer gets bubbled up to the next level, it's going to get added a second time here, and then it's going to add it a third time. And that is how these right here, this sum keeps getting calculated to go up the tree. And then you're just kind of deciding what the best way to calculate it. So the key to this is first figure out how the scoring works, or what the cost of doing that search is, how to calculate it, and make the decision between this. So you want the minimal left subtree plus my current subtree plus the minimal left subtree and the minimal right subtree plus the sum of my current step, so that we can best calculate this. And then from there, the number of subproblems, we have 2 dimensions, I and j. I goes between 1 and n. J goes between I and n. So that is O of n squared. Between this number of subproblems, we are also taking a minimum of k between I and j. So that's another O of n loop. So that gives us O of n cubed runtime. And our final solution is, what is the optimal subtree for the entire list of words, which is from 1 to n. So that is your final value, and the runtime for that is O1. Okay. Student says that the sum of P of I to j took hours to get, and yeah, that is exactly true. That is the tricky part of this problem. Isn't even the actual problem, is understanding the problem. Any questions about this problem? And if you feel uneasy about trying to figure out what this problem is asking, I can say that we try very, very hard not to give a problem that would be this complicated to understand. That you should, even if you don't know how to solve the problem right away, you should at least be able to understand what the problem is asking almost right away in most cases. Okay, Zihao?
So just a quick question on, say, defining initial conditions. For example, for our chain matrix multiplication problems, we have a diagonal matrix. We basically only consider the upper diagonal, and we kind of sort of assume the lower diagonal is 0. Will we get point stalked if we say we just set the lower diagonal to 0? Because that's kind of a kind of vague cop-out, I feel, maybe.
Yeah, I mean, you can set more variables than you need, as long as it doesn't, 1, impact your solution, and 2, does not impact your optimal runtime. Like, that's okay. I mean, right here, right? I have, like, if my subtree makeup is inverted, I have a 0, so that it can easily, like, my diagonal is going to be, my diagonal here is going to be like, let's just make up numbers at this point. And so I'm saying, okay, well, in case, at most, I'm going to look up 1 spot back, so I'm going to set to 0. I mean, I think that's okay. But if you wanted to, like, go even a step further and say, well, I'm just going to set all these to 0s. Like, I don't think that's a problem, as long as it doesn't affect your runtime and it doesn't have any value if you access it. That's fine.
Okay, so as long as we don't go back and try to change it to something else,
yeah,
probably it's fine.
Like, all the rules apply, right? If your answer works and it's optimal, doesn't really matter.
All right, thank you.
Yep. One more question, and then I'm going to move to the next problem. Amasoto?
Yeah, could you explain that sum Pij term again, please?
Okay. So notice here, right? I am going to do 3 times this, right? Because my probability of ending up here when I do a search is the sum of all the probabilities, right? But the cost of coming down here, which is 1, 2, 3, is going to be 3 times that. So this is my cost. My cost of coming down to this level is the probability I'm going to come down to this level times the cost of coming down to this level, right? One way of programming that or encoding that is to always get the sum of that level. So I to j. This is the words I am calculating, and so I'm adding the probability of this, right? I to j. And because that gets set to I of j, right? When I go up a level and I change my window to be larger, I am once again going to calculate the probability of all these windows, right? So let's say I try to show what this is doing. Okay, let's take away the idea that we're trying to calculate the optimum for a moment here. The optimal decision is done by this min. Okay, so let's suppose that all works out. How do we calculate what this T of j is, right, as we go up? So the first thing we're going to do is we're going to say I is equal to here. Okay, so this gives me some number. Okay, right? And then when I go and I look at this number, right here, I'm going to take the sum of this one, and then this one, this one, this one, this one, right? Now, I've already encoded the sum of this number once. So when I go and I check the sum of this number, this is going to be the first time I check the sum of this number, which is 1 times whatever, times 1 time, this will have been calculated twice. It got calculated when I tried this level. It's going to get calculated again when I do this level from the sum of all these words together, right? So this has been calculated twice. This has been calculated once. When I come back up here, I go, okay, what is the sum of all of this together? Again, right? I wanted to figure that. Well, the sum of all this together is this gets multiplied once. This, which is calculated again, having already been calculated once, is now calculated a second time. This having been calculated once by itself, once at this level, and a third time when I take the greater window, this will have been calculated 3 times. So that ends up being your 3, 2, 1 expansion.
Got it. Thank you.
And again, if you don't understand the sum part of this, don't worry about it. You won't see a problem similar to this level of like confusion. Just understand that this is a windowing problem, and this is how you set up a windowing problem.
Okay, because the solution I was able to come up with, like, because I didn't know how to keep track of the 1, 2, 3 levels, so I ended up extending the table by, so it ended up being like n to the 4th one time. So I guess that was suboptimal.
Yeah, what you'll end up doing is you're gonna end up like if you don't encode that going up with the calculation of the sum, every time you do that, you have to calculate all the levels below, and calculating all the levels below instead of encoding it into one of the levels is that you're gonna explode your runtime because you're gonna constantly be calculating that same sum over and over and over again.
Okay, thank you.
Yep. All right, last problem. 6.26. This should really hopefully not be too bad because this is very much a also another really confusing problem, but all right. Sequence alignment. When a gene is discovered, a standard approach to understanding this function is to look through a database of known genes for matches. So you're basically trying to maximize matching. This is an init distance problem. Okay. Formalize this. Think of a gene as being a long string alphabet, and you're trying to see what is the best way you can match these. You get a certain number of points or value if you do match them, a certain number of points if they're mismatched, but the mismatch has different point values depending on what the mismatch is. And then there's another point value if you do a skip. Skips are costly, right? Like you don't want to skip because otherwise you end up costing. So the gap indicates a gap. The characters for each string must appear in order, so they can't be rearranged. Each column must contain a character from at least one of the strings. So you can't do a double gap. You have to do match one of the strings. The score of alignment is specified by the scoring matrix. So we don't know what the scoring matrix is. We just assume we can get that score based on the scoring matrix. With extra row and column to accommodate gaps. For instance, the preceding alignment has the following score. So it decided that it could just do ATGCC match with TAG this, right? But by adding some of these gaps, even though it's costly, it gets you a better match later. Okay. And again, you see how this is a mismatch. This mismatch is not prohibited. It just has some cost to it. Okay. Or some penalty, whatever. Give a dynamic programming algorithm that takes into two strings, a scoring matrix, omega, and returns the highest scoring alignment. Okay. This should be O of mn time. And looking at the O of mn time, you should note that this is kind of an LCS distance type problem. The main thing is that the two strings being compared are different sizes. And so you end up with that runtime. Okay. So this is the solution, and this should immediately jump out at you as, oh, that's the edit distance solution. So our maximum score of 1, 2, ... and y1 to j ... Okay, so we are encoding both I and j's position into our table, and therefore we need a subset of the x string using I and a subset of the y string using j. Okay, anytime you use a variable inside your table for a dimension, you need that to be a subset of whatever you are using. I'm going to skip the base case for now because I think it's important to understand what the recurrence is before we get to the base case, because the base case on this one is, to be honest, really confusing. Okay, so this right here is the edit distance format, right? We have we are trying to take the max such that we are I minus 1, j minus 1, and some functionality of x and y if they match. Then we're going to take x of t of I minus 1j, and we're going to do some function. And we have I and j minus 1, some function. Now, when we are skipping I, we are saying, okay, I'm sorry, when we are skipping the current I, we're saying let's create a gap for that I to match to in the j on the j side. When we are skipping j, we're saying, okay, let us add a gap on the I side for that to match to. Now, we don't know what the scoring function is. It's just saying this is a possibility that a gap is the best solution. Based on, we can assume that if there's a match, this is a very high score. But like I said in the very beginning, right here, this where the heck? This right here indicates the scoring function works on mismatches, right? So we don't know if a mismatch in this particular case is better than a gap on one side or better than a gap on the other side. We don't know how the scoring function works. We just assume that it'll give us the right answer when we call the scoring matrix. Okay. Now, how does this set up our what our base cases are? Okay, similar to how we did the LCS. When I is equal to 1 and j equal to 1, this gives me t of 0, 0, and I need a t of 0, 0 to add to, because the first thing that I want to match against is t of I and t of j. I know that the score is going to be the score of I and j, and that very first match is going to be what that score is. So that base case should be 0. Okay, so that's how that base case is done. Now, I also have to consider I minus